What does the word now actually refer to? Here in the room around you, the answer seems easy. It refers to this moment, the one containing the quiet pressure of the bed beneath you, the faint sounds beyond the walls, and the slow movement of your own breathing. A clock nearby may be changing its numbers 1 second at a time, and everything within reach appears to be changing with it. The room seems to share a present. So does the building around it. Somewhere below or above you, pipes may be cooling, wood may be settling, and another person may be turning in their sleep. All of those things feel as though they belong to the same thin layer of existence. They are happening now. The idea works so naturally at small distances that there is almost no reason to examine it. When you look across a room, light takes a tiny amount of time to reach your eyes, but the delay is much too small for you to notice. You see a chair, a wall, or a hand resting beside you, and you treat what you see as the present. That is a useful habit. It is also where the difficulty begins. Imagine extending this present beyond the room. Let it spread across the building, across the sleeping streets, and over the surface of the earth. Somewhere it is morning. Somewhere it is still yesterday according to the local calendar. Somewhere the sun has not yet risen, while somewhere else it is already high above the horizon. Those differences do not seem important. Time zones are human labels. We can translate one clock into another, and imagine that beneath all the different numbers, the planet shares one real moment. At this instant, Earth has a particular arrangement. Clouds occupy certain places. Oceans have particular patterns of waves. Every moving object has some position, whether anyone is watching it or not. The mind gathers all of this into one planetary now. Then it keeps going. The present stretches past the atmosphere and reaches the moon. It continues through the space between the planets, crosses the orbit of Mars, moves beyond Jupiter and Saturn, and eventually leaves the familiar structure of the solar system behind. Nothing in ordinary intuition tells it to stop. A distant star must be doing something now. A planet circling that star must have a current position. Somewhere in a remote galaxy, gas may be collapsing into new suns, while somewhere else an old star may be nearing the end of its life. The events are far away, but distance does not seem to remove them from the present. They are happening somewhere, and the mind quietly assumes that their moment is the same moment you are experiencing here. One universe appears to require one now. But the universe does not show itself to us that way. When you look at the moon, you do not see it as it is at the moment the light enters your eyes. You see light that left the lunar surface a little more than a second earlier. The moon you observe is already a younger moon than the one that exists when you receive its image. The sun is farther away, so its light takes a little more than 8 minutes to reach Earth. If something changed on the solar surface, no one here could see that change immediately. The information would have to cross the space between the sun and Earth before it could enter a telescope or touch a human eye. The same delay applies everywhere. The light from nearby stars has traveled for years. Light from distant galaxies may have traveled for millions or billions of years. When astronomers look deeply into space, they also look deeply into the past, because distance and delay arrive together. The night sky therefore does not show the universe at one moment. Each point of light comes from a different time. A nearby star may appear as it was a few years ago. Another may appear as it was centuries ago. A faint galaxy may appear as it was before complex life existed on Earth. Yet all of those images reach your eyes during the same evening and seem to form one quiet scene. The scene is real, but it was assembled during observation. Those stars did not all send their light at the same time. Their images began their journeys in different ages and crossed different distances. They become neighbors only when they arrive together at the place where you happen to be. This is not yet a problem for the idea of a universal present. You could still say that everything has a true condition now, even if you cannot see it yet. The sun has a current surface. Every distant planet has a current position. Every galaxy contains some arrangement of stars at this instant, although the light carrying that information may not reach Earth for a very long time. That picture is comforting because it preserves the familiar structure. There is one present, but information about distant parts of it arrives late. This distinction between what exists now and what can be seen now is enough for almost every ordinary situation. If someone is standing across the room, you do not worry that the image reaching you belongs to the recent past. The difference is far too small to matter. Even across the Earth, the delay of light is small enough that technology can create the feeling of immediate contact. Two people separated by an ocean can speak, respond and interrupt one another with only a slight pause. Their conversation feels shared, as though both voices occupy one common moment. The scale of daily life protects the idea of a universal present. Relativity begins to disturb that idea only when we ask how distant moments are actually compared. Suppose two observers are floating far apart in empty space. Each has an identical clock. They are not close enough to place the clocks side by side, but they want to make them agree. To do that, they can exchange light signals. The first observer sends a pulse. The second observer reflects it. The first records when the pulse left and when it returned. If the journey took 10 seconds in total, the first observer assigns 5 seconds to the outward trip and 5 seconds to the return. The reflection is then treated as having occurred halfway between the departure and arrival times. By repeating this process, the observers can synchronize their clocks. Once the clocks have been synchronized, they can assign times to distant events and decide which of those events happen simultaneously. The method seems simple, but it contains an important choice. The observers have defined distant simultaneity by using the behavior of light. At first, that may sound like a technical detail. It is much more than that. Without some procedure like this, the phrase happening at the same time in two distant places has no operational meaning. You cannot directly compare clocks that remain far apart. You need signals, and you need a rule for interpreting those signals. Now imagine a second pair of observers moving steadily past the first pair. They also carry identical clocks. They also exchange light signals. They also find that light travels at the same measured speed in every direction. Their instruments are not damaged, and their calculations are not careless. Yet they do not agree with the first pair about which distant events happen together. The disagreement remains after both groups account for the time that light needs to travel. This point is easy to miss because it differs from an ordinary delay. If you see lightning before hearing thunder, you know the light and sound traveled at different speeds. Once the delay is understood, everyone can agree that both came from the same event. Relativity presents a deeper kind of disagreement. Two observers moving differently can correct for every signal delay and still assign different distant events to the same present. Neither observer has made a mistake. Each has used clocks that work properly. Each has measured light in the same way. Each has built a consistent description of events. The difference comes from motion itself. A moving observer and a resting observer do not divide spacetime into past, present, and future along the same boundaries. The line each one calls now tilts differently through the collection of distant events. Close to the observer, this difference is usually tiny. Over enormous distances, it can become large. Imagine a galaxy so far away that its light requires millions of years to reach Earth. One observer on Earth assigns a particular set of events in that galaxy to the present. Another observer passes Earth at a high speed and assigns a different set of events there to the present. The two observers may stand beside each other for one brief encounter. They may look at the same stars and receive the same ancient light. Yet their definitions of what is happening now in that distant galaxy do not match. This does not mean that the galaxy changes because someone moves. It does not mean that reality depends on opinion. Both observers agree about every event where objects meet. They agree when a signal is sent and when it is received. They agree that one event can cause another only if some influence has enough time to travel between them. They agree about the readings on clocks when those clocks are brought together. Their disagreement concerns distant simultaneity. It concerns which remote event should be paired with the local event they are experiencing here. That pairing feels like a fact of nature, but relativity treats it as part of the observer's frame of reference. The present remains clear nearby. A cup may fall beside you, while a clock ticks and light reaches your eyes, and every observer who meets those local events can agree that they occurred. The difficulty appears when the word now is stretched over a distance. To extend a local present across the universe, an observer must decide how distant clocks are synchronized. Another observer moving differently makes that extension in a different way. The universe does not appear to select one of them as the hidden correct choice. There is no visible master clock outside the cosmos keeping one official time for every place. This is uncomfortable, because the mind wants the present to be something more than a method of organization. The past feels absent, the future feels unfinished, and the present feels physically special, as though existence itself is concentrated in a moving boundary between what has happened and what has not. Relativity does not remove your immediate experience of that boundary. You still inhabit a local moment. Your thoughts occur in an order, your body changes. A clock beside you records a sequence. What relativity removes is the assumption that your local boundary continues unchanged across all of space. The present may not be a single sheet passing through the universe. It may be something that each observer constructs around a local path. This becomes easier to understand if we stop imagining clocks as devices that measure a substance called time flowing everywhere. A clock records change along its own journey. An atomic clock counts regular transitions inside atoms. A pendulum clock counts swings. A mechanical watch counts the motion of gears and springs. Your body keeps rough time through chemical cycles, temperature, hunger, fatigue, memory, and the repeating alternation of waking and sleep. Each clock stays with something. It follows a path through the world and records what happens along that path. When two clocks remain together, they can agree. When they separate, each continues measuring its own sequence. If they later meet again, their readings can be compared directly. That comparison is local. Both clocks are present at the same event in the same place. The idea of a universal now asks for more. It asks us to compare clocks that may never meet, assign times to events too distant to observe directly, and imagine one cosmic arrangement containing everything at once. Relativity allows us to perform that construction. It simply does not give us only one way to do it. The room around you has not changed. It still feels quiet and shared. The objects nearby still appear to occupy the same moment, and for every practical purpose they do. But that peaceful local present may not extend as far as it seems. Beyond the room, beyond Earth, and beyond the solar system, the word now begins to depend on how an observer is moving and how distant clocks have been compared. So the question we started with needs to be adjusted. We asked what is happening right now on the other side of the universe. Relativity asks us to specify which observers now we mean. That does not answer the question. It reveals that the original question was carrying an assumption, one so familiar that it had disappeared inside the language. We assumed the universe came with one present already attached. The next step is to see exactly how that assumption fails. We will place clocks along a line, send light between them, and let two observers pass through the same experiment at different speeds. Nothing will malfunction. No signal will be lost. Every clock will behave exactly as it should. And the two observers will still build different versions of the present. Imagine a railway platform extending through the night. The platform is perfectly straight, and a train is moving beside it at a steady speed. There is no vibration in the rails, no wind pressing against the carriages, and no nearby landmark that would make one direction feel more important than another. Inside the train, the ride is smooth enough that a passenger could close their eyes and forget the train was moving. Outside, an observer stands at the exact middle of the platform. At one carefully chosen moment, two flashes of light appear. One comes from a point far to the left. The other comes from an equally distant point far to the right. The platform observer is standing halfway between them. The light from both flashes crosses the same distance and reaches the observer at the same moment. Because light travels at the same speed from both directions, the observer concludes that the flashes occurred simultaneously. For the platform, the two events belong to one present. Now consider a passenger standing at the exact middle of the moving train. At the instant the flashes occur, the passenger is beside the platform observer. Their positions briefly coincide, but the train continues moving while the light travels toward them. The passenger moves toward the flash, coming from the front of the train, and away from the flash, coming from the rear. The forward flash therefore reaches the passenger first. The rear flash arrives later. At first, this sounds like a simple difference in travel time. The passenger moved toward one beam and away from the other, so of course the beams arrived at different moments. Perhaps the passenger can correct for that motion and recover the platform observer's conclusion. That is what ordinary intuition expects. But the passenger also measures light traveling at the same speed in both directions. This is the part that cannot be replaced with the older picture of motion. If someone runs toward a slowly moving object, the closing speed changes. If two boats move toward each other across still water, each approaches the other faster than either boat moves relative to the water. Light does not behave that way. The passenger does not measure the forward beam as moving more quickly because the train is approaching it. The passenger also does not measure the rear beam as moving more slowly because the train is moving away from it. Both beams move at the same measured speed. The passenger is standing halfway between the front and rear of the train, and light travels equally fast from both ends. Since the forward light arrives first, The passenger concludes that the forward flash must have happened first. The platform observer says the flashes were simultaneous. The passenger says the flash at the front occurred earlier. Neither conclusion comes from poor eyesight or a slow instrument. Each observer uses the same rule. Each is positioned at the midpoint of their own system. Each measures the same speed of light in both directions. They disagree because their systems of synchronized clocks do not agree. To see this more clearly, imagine that the platform is lined with clocks. There is one clock beside every section of track. All of them have been synchronized using light signals. When a pulse is sent from the middle of the platform, clocks at equal distances receive it together and set themselves according to the agreed procedure. The platform now possesses a network of clocks. Every event beside the railway can be assigned a place and a time. The two flashes occur beside different clocks, but both clocks display the same reading. That is what the platform observer means when saying they were simultaneous. The train also contains a line of clocks. One clock is mounted in each carriage. The passengers have synchronized these clocks while remaining at rest relative to the train. From their point of view, their procedure is completely symmetrical. Light travels through the train at the same measured speed in both directions, and clocks at equal distances from the center are set to agree. The passengers therefore possess their own network. When the train passes the platform, each train clock briefly moves beside one platform clock. At those meetings, the two readings can be compared directly. Near the center, one pair may agree. Farther along the track, they do not. The platform observer finds that clocks toward the front of the moving train are set differently from clocks toward the rear. The passengers make the corresponding judgment about the platform clocks. Each group sees the other group's distant clocks as out of synchronization. This is not because either group performed the procedure incorrectly. Synchronization belongs to the frame in which the clocks are at rest. A collection of clocks synchronized across the platform is not synchronized in the same way when described from the moving train. A collection synchronized across the train is not synchronized in the same way when described from the platform. This is the hidden machinery beneath the disagreement about the flashes. The two observers do not merely receive the same events at different moments. They assign different times to the events after correcting for light travel, and after consulting their own synchronized clocks. For the platform, the flashes share one time. For the train, they do not. It helps to slow the scene down and remove the word observer for a moment, because that word can make the result sound psychological. Nothing depends on what a person sees. The people could be replaced by cameras, atomic clocks, automatic detectors, and computers. The detectors would register the same arrival times. The clocks would record the same readings. The disagreement would remain after every number was collected. The effect belongs to the geometry of the situation. An observer is only a convenient name for a complete reference system containing clocks, rulers, and a method for assigning coordinates to events. The platform is one such system. The train is another. Each system divides the same collection of events into layers of equal time, but those layers do not line up. You can picture the platform's present as a long horizontal line passing through every platform clock that shows the same reading. One instant later, another horizontal line appears, then another. In the train's description, the lines of equal time are tilted relative to those of the platform. A single event at the middle may lie on both observers' present lines. Far away from that meeting point, the lines separate. One observer's present includes events that another places slightly in the past. It also includes events that the other places slightly in the future. At ordinary speeds and ordinary distances, the separation is extremely small. A train moving along a real railway does not create a noticeable disagreement about events at the ends of a carriage. The difference exists, but it is far below the sensitivity of ordinary human experience. That is why the old idea of simultaneity survived so easily. For almost everything people once measured, the disagreement was too small to matter. Clocks could be treated as though one universal time passed through all of them. Motion changed position, but it did not seem to alter which distant events belonged to the present. Relativity becomes visible when the speed is large, the distance is large, or the clocks are precise enough. Imagine the train moving at a substantial fraction of the speed of light. Imagine that it is no longer a train but a vast spacecraft, long enough for light to require a noticeable time to cross it. The difference between the two systems would no longer hide inside tiny fractions of a second. The spacecraft crew could synchronize clocks throughout the vessel and use them to describe distant events. Observers at rest relative to a nearby planet could do the same. Both groups would produce consistent records. But their sheets of equal time would cross the surrounding universe differently. Now increase the distance. Instead of asking which flashes occur together at opposite ends of the spacecraft, ask which events in a remote star system occur at the same time as one local event. A small change in the observer's motion can shift the assigned distant present by a much larger amount because the line of simultaneity extends across an enormous distance. The observer does not make the distant event happen. The shift does not send information backward or forward through time. No message travels instantly from the observer to the star. What changes is the event selected by the phrase "happening now" over there. This distinction matters. Relativity does not allow an observer to alter the distant world merely by changing speed. It changes how the observer's coordinates arrange events that already belong to spacetime. Events that can influence one another retain their causal order. If one flash sends a signal that later reaches a detector, every observer agrees that the flash came before the detection. The amount of time and distance assigned between them may differ, but the cause does not become the effect. The disagreement about order occurs only for events separated so widely that no light signal could travel from one to the other in time. Neither event can cause the other. For such separated events, different observers may disagree about which occurred first, or whether they were simultaneous, without creating a contradiction. Consider two distant stars that brighten during the same period. In one reference frame, the star on the left brightens first. In another, the star on the right brightens first. In a third, the two brighten simultaneously. This sounds impossible only if the universe contains one hidden time order for every pair of events. But these two brightenings cannot affect each other. Light from one does not have enough time to reach the other before it changes. Their order has no causal consequence. When the light from both stars eventually reaches a detector, all observers can agree about the readings recorded at that meeting. They can calculate how their coordinate systems differ. They can translate one description into another. No physical fact has become inconsistent. The only thing that failed was the expectation that every event in the universe could be placed in one universal sequence. There are local sequences. A clock records one event after another along its path. A person remembers waking before walking into another room. A star forms before it exhausts its fuel. A signal leaves before it arrives. These orders remain meaningful because the events can be connected by physical influence. But two distant events with no possible causal connection are not always provided with an absolute order. The universe gives us more structure than a random collection of happenings, but less structure than the universal timeline our intuition expects. The platform observer can say that the flashes occurred together. The passenger can say that one occurred first. Both statements are complete only when the reference frame is included. This is similar to saying that one object is to the left of another. The statement needs an orientation. Turn around and left changes into right. The objects have not changed, but the coordinate description has. Time order feels more fundamental than left and right, so the comparison can seem unsatisfying. You can turn around in space. You cannot turn around and walk into yesterday. But relativity is not saying that every temporal distinction is a matter of perspective. It is saying that distant simultaneity behaves more like a spatial relation than we once believed. The division between space and time has begun to soften. Motion through space changes how distant time is assigned. A different velocity does more than alter where an observer will be later. It changes the angle of the observer's present across space-time. This is the first sense in which time and space exchange part of their roles. What one observer describes as purely spatial separation between simultaneous events, another describes as a mixture of spatial separation and temporal separation. The events remain the same. The interval between them remains part of the same physical structure. But the amount assigned to space and the amount assigned to time depend on how the observer is moving. This does not make time identical to space. There are still important differences between them. You can choose a direction through space in ways you cannot choose a direction through time. Causal influence places limits on which events can be reached. A clock follows one kind of path through space-time, not every path that can be drawn. But the old picture of separate containers is already failing. Space is no longer one fixed stage carrying objects from place to place while time flows independently behind it. Measurements of space and time are connected. Change the motion of the observer, and the division between them changes too. The clocks along the platform define one present. The clocks inside the train define another. Neither present reaches beneath the other to reveal a hidden universal layer. They are two valid ways of cutting through the same space-time. For someone resting quietly in a room, none of this needs to be felt. The nearby world continues to share an almost perfect common time. The differences are too small to disturb a breath, a heartbeat, or the soft changing numbers on a clock. Yet the clock beside you is not measuring the time of the whole universe. It is measuring time along one local path. Another clock moving differently follows another path and constructs a different network of distant moments around itself. The question now becomes more precise. If there is no universal present connecting all places, what does a clock actually measure as it travels? The answer will not be a coordinate assigned from far away. It will be something carried by the clock itself, accumulated along its journey, and revealed when two separated paths finally meet again. The two clocks meet again at the center of the experiment. For a brief moment, the clock carried by the moving observer passes directly beside the clock resting on the platform. Their displays can be compared without sending a signal across any distance. Whatever disagreement existed between their wider systems of clocks, this meeting is local. Both clocks are present at the same event. That word, event, is going to become useful. An event is something that happens at one place and one time, such as a flash appearing, a detector clicking, two clocks passing beside each other, or a particle striking a screen. The birth of a star is spread over a long process, but any single collision inside that process can still be treated as an event. Events do not belong to one observer. Different observers may assign different coordinates to them, just as two maps may use different grids for the same mountain. But the event itself remains where the descriptions meet. If two objects collide, everyone agrees that the collision occurred. If a light signal leaves one clock and later reaches another, everyone agrees about the departure and arrival. The disagreement begins between events. Suppose one flash occurs near a distant star and another flash occurs near a different star. The stars are so far apart that light from either flash could not reach the other before both have already happened. No influence connects them. The first flash cannot trigger the second cannot prevent the first. Whatever produced each event had to arise from conditions already present nearby. These events are separated in a way physicists call space-like. The name sounds technical, but the idea is simple. The distance between the events is too great, and the time between them is too short for light or any slower influence to travel from one to the other. Because no signal can connect them, nature does not require every observer to agree about their order. One observer may say the left flash happened first. Another may say the right flash happened first. A third may say they happened at the same time. All three descriptions can be valid. This does not allow a cause to occur after its effect. The flashes cannot cause each other in any description. Their order can change because nothing physical travels between them. The situation is different when one event can influence another. Imagine a pulse of light leaving Earth and later reaching a spacecraft. The departure and arrival are connected by the pulse itself. Every observer agrees that the light was sent before it was received. They may disagree about the distance the pulse crossed. They may disagree about how much coordinate time passed. They may even disagree about whether the spacecraft or Earth should be treated as moving. But no valid observer places the arrival before the departure. Events joined by light preserve their order. Events joined by a slower object preserve it too. If a spacecraft leaves one planet and later lands on another, no observer can reverse the departure and landing. The craft traces a continuous path from one event to the next. This gives spacetime a partial order. Some events are clearly earlier than others because a signal or object can connect them. Some are clearly later, but many distant pairs are not given an absolute order at all. The universe does not arrange every event in one complete sequence. That is not how time feels. Your own life arrives as a sequence. One breath follows another. A sound begins and fades, a thought appears, changes, and is replaced by another thought. You remember earlier events and wait for later ones. Along your own path, order remains firm. The clock beside you records one reading after another. Your body occupies one local event, then another. Every event you could personally visit lies somewhere along a continuous route through space-time. This route is called a world line. The name can create the image of a thin mark drawn through a diagram, but the line represents something very ordinary. It is the complete history of an object. A clock resting on a table has a world line. A planet orbiting a star has a world line. A photon crossing a room has a world line, though light follows a special kind of path. Your own world line passes through every event in which you have taken part, from moments too early to remember to the quiet moment in which you are listening now. The order along that line cannot be rearranged by changing observers. Someone moving past you may assign different coordinates to the events of your life, but they will not place tomorrow before yesterday. Every observer agrees on the sequence of events that can be connected along your path. The missing universal present does not dissolve local time. It changes how separate world lines are compared when they are far apart. Imagine two observers passing each other in deep space. At the moment they meet, both set their clocks to the same reading. Afterward, one continues in one direction and the other continues in another. Each carries a row of imagined clocks at rest relative to their own motion. Each uses light signals to define which distant clocks are synchronized. At their meeting event, their presents overlap. Both include the same local point. But as their definitions of now extend outward, they separate. One present tilts one way through spacetime, the other tilts another way. Nearby, the difference is tiny. Far away, the difference grows. This is why relativity of simultaneity is easy to ignore in daily life and difficult to ignore when thinking about the cosmos. A small difference in motion can correspond to a substantial difference in which remote events are included in the present, provided the remote location is far enough away. The effect is not transmitted across space. Nothing reaches the distant location when the observer changes speed. The observer is not altering the remote world. Only the selection changes. The observer is changing which distant event is paired with the local event called now. This pairing was never carried by a physical signal. It was produced by the observer's system of synchronized clocks. Imagine a long book containing every event that occurs in a distant galaxy. One observer's present intersects one page of that book. Another observer's present intersects a nearby page. The galaxy does not jump between pages. Both pages are already parts of the full spacetime description. What differs is the cross-section each observer calls simultaneous with the local moment. This comparison can be misleading if the book is taken too literally. A book exists all at once on a shelf, while our experience of time does not feel like that. We do not look across completed pages of our own future. Still, the image captures one feature of relativity. A present is not chosen by the distant galaxy alone. It depends on the relation between that galaxy and the observer assigning the time. For centuries, time was treated as though it provided a universal ordering before anything happened. Every event could be placed somewhere on one master timeline. First came one event, then another, whether the events occurred beside each other or on opposite sides of the universe. Relativity keeps the order where physical influence can establish it. It does not keep the order everywhere else. This can feel like the loss of something necessary. If distant events have no single order, perhaps reality itself becomes uncertain. But uncertainty is not the right word. The events and their relationships remain definite. Light still connects some events and fails to connect others. Objects still follow continuous paths, and clocks continue accumulating readings. What disappears is one extra layer we expected to find, a universal sequence covering even events that could never affect one another. The theory removes that layer without removing the events. Consider three flashes in empty space. The first flash sends light to the second. The second sends light to the third. Every observer agrees that the first occurs before the second and the second before the third. Their causal connection holds the order in place. Now add a fourth flash so far away that none of the first three can reach it before it occurs. Where should it be placed in the sequence? One observer may place it between the first and second. Another may place it between the second and third. Another may place it before all three. No contradiction appears because the fourth flash cannot participate in the chain. It cannot interrupt the signals, prevent them, or be produced by them. The complete sequence existed only in the observer's coordinates. The causal chain existed in the events themselves. This distinction is one of the quiet changes relativity makes to the word reality. Reality is not a list sorted into one universal order. It is a structure of events connected in different ways. Some connections are causal, some are spatial, some paths can be followed by matter, Some can be followed only by light. Others would require motion faster than light, and therefore cannot carry any known influence. Observers describe the same structure from different states of motion. Their coordinates differ, but the allowed connections do not. A spacetime diagram makes the idea visible. Imagine time rising upward on a page and one direction of space extending from left to right. Your world line moves upward because your life passes from earlier events to later ones. If you remain in one place, the line appears almost vertical. If you move through space, it leans to one side. Light traces diagonal paths. A flash spreads in both spatial directions as time moves upward, creating the edges of a widening cone. Events inside the future portion of that cone can be reached by signals sent from the flash. Events inside the past portion could have sent signals to it. Events outside both regions are too far away to be connected in time. Those outside events are the ones whose order can change between observers. Different observers draw different horizontal directions for equal time. One observer's present passes through one group of space-like events. Another observer's present passes through another. But both preserve the light cone. They disagree about the distant present while agreeing on what can affect what. This is why causality survives when simultaneity does not. The shape of the cone changes in appearance under different coordinate systems, but its boundary continues to separate possible influence from impossible influence. No ordinary observer can tilt their path beyond the path of light. A massive object can move through space, but its world line must remain inside the local light cone. It can change speed, turn around, or accelerate, yet every step must remain connected to the next by a physically allowed path. Your present may tilt differently from another observer's present. Your future light cone does not become their past light cone. The boundary keeps cause and effect from exchanging places. So there are two kinds of order hiding inside the everyday word time. There is causal order, the order preserved by signals, interactions, and world lines. Then there is coordinate order, the wider arrangement created when an observer assigns times to distant events. The first is shared. The second depends on motion. In daily life, the two seem to merge because signals move quickly compared with the distances involved. Almost every event you care about is close enough that disagreements in distant simultaneity are negligible. You can say that two people entered nearby rooms at the same time, and the statement has a practical meaning. The correction required by relativity is far too small to affect anything human beings normally notice. Across astronomical distances, that convenience weakens. The phrase "at the same time" begins to carry the observer's state of motion inside it. There is no need to stop using the phrase. Physics often keeps ordinary language and gives it a more careful definition. Temperature remains useful even though it emerges from microscopic motion. Sunrise remains useful even though Earth is turning. Simultaneous remains useful when the frame of reference is understood. The mistake would be to imagine that the frame can always be removed. Suppose an observer beside Earth asks what is happening now near a distant star. The question has an answer within the observer's chosen frame. A second observer moving relative to Earth also has an answer. The two answers may refer to different events near the star, and neither is more real merely because one observer happens to be closer to Earth. If the observers later compare calculations, each can translate the other's answer into their own coordinates. The difference is orderly and exact. Relativity does not produce chaos. It replaces one universal description with a family of descriptions linked by precise rules. Every observer can recover what the others measured. No observation becomes private. No event belongs to one mind. The universe remains objective even when simultaneity is relative. That point matters because the word relative is often mistaken for arbitrary. The observers cannot choose any answer they like. Their motion determines the relationship between their clocks. The speed of light constrains the synchronization procedure. The geometry fixes how one coordinate system converts into another. The freedom is structured. A compass direction depends on orientation, but it is not arbitrary once the orientation is known. In the same way, distant simultaneity depends on motion, but the result is fixed once the motion and coordinates are specified. Two observers, two presents. Not because reality has divided into two universes, and not because human perception creates the events, but because there is no single observer-independent way to join distant events into one moment. The place where the observers meet remains shared. The light they exchange remains shared. The readings on their clocks at each meeting remain shared. Their extended presence do not. And this brings us back to the small clock carried beside one observer. If that clock does not measure the time of the whole universe, it must measure something more local. It counts the duration along its own world line. Another clock can leave, travel through a different region of space-time, and return. When the clocks meet again, their displays may no longer agree, even though both worked perfectly throughout the journey. The disagreement will no longer concern distant simultaneity. It will be written directly on the clocks at one shared event. To understand that result, we have to follow the clocks as they take different roads through space-time. Imagine two identical clocks resting beside each other in a quiet spacecraft. They were built in the same laboratory, from the same design, and checked against each other until no measurable difference remained. One clock stays inside the spacecraft. The other is carried away on a smaller vessel, travels through empty space, turns around, and eventually returns. When the clocks are placed together again, they no longer show the same reading. Nothing has broken. The traveling clock has not lost time in the way an old watch might run slowly because its mechanism is damaged. Every process inside it has unfolded normally. If a person had traveled beside that clock, their heartbeat, breathing, thoughts, and metabolism would have remained synchronized with it. They would not have felt time becoming sluggish. The clock that stayed behind also behaved normally. Yet fewer seconds have passed along one journey than along the other. This is no longer a disagreement about distant events. The clocks have returned to the same place. Their readings can be compared without correcting for signal delays or asking how distant clocks were synchronized. The difference is present on the displays. Each clock has measured the length of its own path through space-time. Physicists call this measured duration proper time. The name can sound as though one clock has found the proper correct time while the other has measured an inferior version. That is not what it means. Proper time is simply the time recorded by a clock that travels along a particular world line. Every clock has its own proper time. The clock beside you records the duration along its path, through the room, through Earth's rotation, through Earth's orbit around the Sun, and through the motion of the solar system within the galaxy. You do not notice those wider motions because the clock travels with you. Locally, it seems to be at rest. Its seconds are ordinary seconds, and every physical process nearby shares them closely enough for daily life. Another clock may follow a different path. If the two clocks separate and later reunite, they can accumulate different amounts of proper time between the same departure and reunion events. The idea becomes clearer with an imaginary clock made entirely from light. Place two perfect mirrors opposite each other. Send a pulse of light upward from the lower mirror. It reaches the upper mirror, reflects, returns to the lower one, and repeats. Each round trip is one tick. For someone moving beside the clock, the light travels straight up and down. The mirrors remain in the same positions relative to that observer, and the pulse follows the shortest visible route between them. Now imagine watching the same light clock pass from left to right. While the pulse moves upward, the entire clock moves sideways. By the time the light reaches the upper mirror, that mirror has shifted to the right. The light therefore follows a diagonal path. On the return journey, it follows another diagonal path to reach the moving lower mirror. From your perspective, the light travels farther during each tick. But you still measure light moving at the same speed. If the distance is greater and the speed cannot increase, each tick must take more time according to your clock. The moving light clock ticks more slowly relative to you. The person traveling beside it does not observe this slowing. To them, the pulse continues moving vertically between the mirrors, and their own clock ticks normally. Instead, they say that your moving clock is the one running slowly. As long as the two observers continue moving steadily apart, the situation is symmetrical. Each can treat themselves as resting. Each can describe the other as moving. Each can say that the other clock accumulates time more slowly between comparisons made through exchanged signals. This symmetry is sometimes presented as a contradiction. If each sees the other clock running slowly, how can the clocks ever reunite and reveal one definite difference? The answer is that they cannot reunite while preserving the symmetry. One of them must change direction. The traveling clock leaves, turns around, and returns. The clock that stayed behind does not follow the same sequence of motion. The paths are different. The traveler may spend long periods moving at a steady speed, during which either observer can describe the other as moving. But the full journeys are not interchangeable. The traveler changes from one state of motion to another in order to come back. Acceleration reveals this asymmetry, although the final age difference does not depend only on how forceful the turnaround feels. The important fact is that the clocks followed different world lines between the same two meetings. They departed at one event. They reunited at another. Between those events, one path went outward and returned, while the other remained comparatively direct. In ordinary geometry, a straight path between 2 points is the shortest distance. Spacetime geometry behaves differently. For the kinds of paths followed by objects moving slower than light, the unaccelerated path between two events accumulates more proper time than a path that leaves it, changes direction, and returns. The clock following the straighter world line records more time. This reversal of the familiar geometric rule is one reason spacetime cannot be treated as ordinary space, with an extra direction added casually. The time dimension enters the geometry differently from spatial dimensions. A traveler can therefore return younger than someone who remained behind. The word younger often gives the thought experiment an artificial feeling, as though the effect belongs only to imagined twins and impossible spacecraft. But there is nothing special about human aging in the result. Every physical process follows the clock. A radioactive sample carried by the traveler would undergo less decay. A mechanical device would complete fewer cycles. A living body would experience fewer heartbeats and chemical changes. The traveler would not merely look younger, because light from them arrived late. They would have lived through less proper time between departure and reunion. The difference would be small at ordinary speeds. A person traveling by aircraft experiences a difference far too small to notice without precise instruments. But atomic clocks are sensitive enough to measure changes caused by motion, and experiments have repeatedly found the effect predicted by relativity. Clocks carried or operated under different conditions do not accumulate identical readings merely because they began together. This tells us something important about what a clock is doing. A clock does not measure an invisible universal substance flowing past it. It measures duration along a path. The journey matters. That may feel strange because distance also depends on the path. Walk directly across a room and you cover one distance. Walk around its walls first and you cover more. The beginning and ending places can be identical while the distance traveled differs. Proper time has a similar path dependence, but the geometry is not the same as ordinary distance. Two clocks can leave the same event, reunite at the same event, and carry different durations between them. Neither duration is an illusion. Neither needs to be corrected into a hidden master time. Each clock has measured the route it actually followed. Imagine the traveler looking through the spacecraft window during the outward journey. Earth appears to recede. Signals from Earth arrive increasingly delayed, and their frequency is affected by the changing separation. During the return journey, signals arrive differently again. The visual appearance can become complicated because what the traveler sees combines time dilation with the travel time of light. But proper time does not depend on appearances. The traveler can ignore the window entirely. Their clock continues counting local seconds. The observer on Earth can do the same. When they meet again, the accumulated readings settle the result. Relativity distinguishes carefully between the image received from far away and the time a local clock records. A distant clock may appear slowed for several reasons. Its light may have taken longer to reach you. The source may be moving away, stretching the arrival of successive signals. Gravity may also affect the comparison. Those effects must be separated when distant observations are analyzed. Proper time avoids that ambiguity at the meeting point. Two clocks beside each other can be compared directly. The difference in their readings records the difference in their histories. This is why clocks are more than instruments placed inside spacetime. Their behavior reveals the geometry of spacetime. A ruler can trace spatial distance along a surface. A clock traces temporal distance along a world line. If the geometry changes, the relationship between clocks changes. If the paths change, the accumulated time changes. The traveler's clock is therefore not a flawed copy of the clock that stayed behind. It is a record of another route through reality. The journey can be divided into small segments. During each segment, the traveler has a local frame in which their clock is at rest and behaves normally. Add all of those local durations together, and they form the proper time of the full journey. The observer who stayed behind can also divide their world line into small segments and add the durations. The totals need not agree. Each second remains locally ordinary. The difference emerges only when the full paths are compared. This makes the result less dramatic and more unsettling. There is no moment during the journey when the traveler feels that time has been taken away. There is no missing interval. Nothing skips. One thought follows another, meals are eaten, sleep comes and ends, and the traveler's clock completes each tick at its usual local rate. The smaller total appears because the route through spacetime contains less proper time between the shared endpoints. A person cannot feel their own proper time slowing because every instrument available to them slows in the same comparison. Their brain, clock, and body all travel along the same world line. To feel a change, they would need access to a second local process that did not share the same spacetime path. But anything beside them shares it. Local physics remains normal. Relativity becomes visible through comparison. This is also why the phrase "time slows down" can be helpful but incomplete. Nothing resembling a fluid has thickened around the traveler. Their seconds have not become defective. The statement means that when two clocks follow specified paths and their readings are compared, one path contains less elapsed proper time. The geometry predicts the difference. The clocks reveal it. The same idea applies beyond ideal spacecraft. Particles created high in Earth's atmosphere can move at speeds close to that of light. Their behavior when detected near the surface agrees with relativistic time dilation. Precision clocks moving at different velocities show corresponding shifts. The effect is part of the working physics used to compare modern timekeeping systems, not a philosophical decoration added to the theory. Still, the thought experiment with two travelers contains something the laboratory result can hide. It shows that time is personal without being subjective. The traveler has their proper time. The person who stayed behind has another. The values depend on physical paths, not opinions or feelings. Anyone who knows the world lines can calculate the same result. No observer gets to choose how much time the clocks record. The duration belongs to the geometry. This gives a more careful meaning to the sentence that time belongs to the observer. It does not mean each mind creates its own universe. It means every physical observer follows a world line, and an ideal clock traveling on that world line measures its proper time. Different world lines can contain different durations. The universe does need one clock whose reading every other clock imperfectly copies. It needs only local clocks and rules for comparing them. The departure event joins the clocks. Their separate journeys pull their histories apart. The reunion brings them together again and makes the difference visible. Between those meetings, each clock carries its own answer. Now return to the room around you. The clock nearby is following an almost unimaginably complex path. Earth rotates beneath it. The planet moves around the sun. The sun moves through the galaxy. The galaxy itself participates in larger motions. Yet none of these motions can be turned into one absolute speed through space. Speed is always measured relative to something else. The clock's proper time does not require a stationary background. It requires only the path encoded by spacetime and the local physical processes that count along it. This is where the old image of time as a river becomes difficult to maintain. A river flows past every object according to one shared current. An object may move through the water differently, but the water itself provides a background against which all motion can be judged. Relativistic time offers no such current. There are world lines. There are intersections where clocks meet. There are light signals connecting events. There are durations measured along paths. The clock does not dip into a universal flow and report how much passed. It reports the temporal length of its own journey. And once duration becomes a property of paths, space and time can no longer remain separate accounting systems. Motion through space changes the amount of time measured between meetings. A difference in spatial route becomes a difference in temporal duration. The next question is therefore not merely why the traveling clock records less. It is what kind of geometry can combine motion, distance, light, and elapsed time into one structure, while allowing every observer to describe the same events consistently. That structure is space-time. Inside it, a clock is not standing outside reality and measuring its passage. The clock is moving through the shape it measures. A clock is moving through the shape it measures. That sounds strange only because we usually imagine geometry as something that belongs to space alone. A room has length, width, and height. A road has distance. A planet has a circumference. Time seems to belong to a different category, something that passes while objects move through the geometry around them. Relativity joins these measurements more closely. To see why, return to the two identical clocks. They separate at one event and meet again at another. One clock remains on the more direct path. The other travels outward, changes direction, and returns. When they meet, both clocks are working properly, but they display different totals. If time were independent of space, the route through space should not affect the elapsed time. Both clocks began together and ended together, so one universal time should have passed between those meetings. But that is not what the clocks record. Their spatial journeys and temporal readings are connected. The simplest way to describe that connection is to treat each event as having both a position and a time. An event is not fully located by saying where it happened, because the same place can contain an unlimited number of events. Your room yesterday is spatially close to your room now, but the two moments are not the same event. It is also not enough to say when something happened, because many events can share the same clock reading within a chosen reference frame. A flash on Earth and a flash near a distant spacecraft may be assigned the same time while occurring in very different places. An event needs both kinds of information. Where it happened. When it happened. Together, those coordinates place the event in spacetime. The word spacetime can make the idea sound more mysterious than it is. It means that space and time cannot always be separated in a way every observer shares. One observer divides the separation between two events into a certain amount of space and a certain amount of time. Another observer moving differently produces another division. The observers may disagree about both parts, but a deeper combination of the measurements remains the same. That combination is called the spacetime interval. In ordinary geometry, the distance between 2 points can be calculated from their separation in different directions. If one point lies 3 units to the side and 4 units upward from another, the direct distance between them is 5 units. The answer does not depend on how the page is turned. Rotate the coordinate grid, and the horizontal and vertical components change, but the direct distance between the points remains 5 units. Different observers can use different axes and still recover the same underlying separation. Spacetime has an interval that plays a related role. Observers moving differently disagree about the spatial distance and elapsed coordinate time between two events. Yet when those pieces are combined according to the geometry of relativity, they agree on the interval. For events connected by a clock moving slower than light, this interval corresponds to the proper time recorded by that clock. The clock's reading is therefore not a coordinate convention. It is something every observer can calculate from the path, even when they describe the space and time parts differently. Imagine watching a spacecraft pass from left to right. You say the craft is crossing space while your clocks continue ticking in the laboratory. Someone inside the craft says they are at rest while the laboratory moves in the opposite direction. The two descriptions divide space-time differently. You assign more of the separation between certain events to space. The traveler assigns more or less of it to time, depending on the events being compared. But both of you calculate the same proper time along the spacecraft's world line. This is how relativity keeps an objective structure without keeping absolute space or absolute time. It does not say that every measurement is equally true without restriction. It says that certain components depend on the observer, while the interval connecting them does not. A familiar object can help. Imagine a long walking stick lying on a floor. One person aligns a coordinate grid with the stick and says its full length lies along the horizontal direction. Another person uses a grid turned at an angle. For the second person, the stick has both a horizontal and a vertical component. The components differ because the grids differ. The stick does not. Relativity applies a more unusual version of this idea to space and time. Changing velocity is somewhat like rotating the coordinate grid through space-time, though the geometry does not behave exactly like an ordinary rotation on a floor. What appears as a certain mixture of space and time to one observer appears as another mixture to someone moving differently. This is why motion changes the measured length of objects and the rate of separated clocks. Those effects are not unrelated distortions added to the theory. They come from the same transformation between space-time coordinates. Consider a rod moving past you. You measure the position of its front and rear at the same time in your reference frame. That requirement matters. To measure its length, you must compare both ends simultaneously. But the moving observer does not agree that your two measurements occurred at the same time. Your definition of length already contains your definition of distance simultaneity. Since another observer uses a different simultaneity, they divide the same spacetime events into space and time differently. Length contraction and relativity of simultaneity are therefore connected. So is time dilation. A moving clock follows a world line tilted through your spacetime coordinates. Between two of your time slices, the clock has moved through space as well as time. The geometry assigns a different amount of proper time to that path than to the path of a clock resting beside you. The effect does not arise because the moving clock is mechanically strained by motion. It arises because the two world lines have different spacetime lengths. This language of length has to be handled carefully, because temporal length behaves differently from spatial distance. Suppose two people leave the same point in a city and meet later at another point. In ordinary space, the person who takes a winding route travels farther than the person who walks directly. Between two time-like events in flat spacetime, the unaccelerated clock takes the path with the greatest proper time. A clock that leaves that path changes velocity and returns records less. This is the geometric heart of the traveling clock result. The direct world line is not merely a convenient route through a pre-existing flow of time. It is the path that contains the largest amount of proper time between those two events. The comparison can be drawn on a spacetime diagram. Place the departure event near the bottom and the reunion event higher on the page. The clock that remains at rest follows a straight vertical line between them. The traveling clock follows a line that leans outward and then turns back inward. Both paths begin and end at the same events. On ordinary graph paper, the bent path looks longer. In spacetime geometry, it contains less proper time. The traveler returns with a smaller clock reading. The result is not caused by the drawing. The diagram is only a way of representing the invariant interval that the clocks physically measure. This is one reason the phrase time is the fourth dimension needs some care. Time is part of a four-dimensional spacetime description. Three coordinates locate an event in space and another locates it in time. But time is not simply another spatial direction. The spacetime interval combines temporal and spatial separations with different signs. That difference changes the geometry and separates possible physical paths from impossible ones. A person can turn toward the left or right in space. They cannot turn toward the past in the same way. A massive object can follow many world lines, but all physically possible local paths remain inside the boundaries drawn by light. Those boundaries appear because light has a special interval. Take two events connected by a pulse of light. Every observer measures the pulse moving at the speed of light, even though they may disagree about the distance it travels and the coordinate time it takes. For light, the spatial and temporal parts of the interval balance in a special way, giving a spacetime interval of 0. This does not mean the two events are identical. The light may cross a room, a planet, or the distance between stars. It means that the path lies exactly on the boundary separating events that can be joined by slower matter from events that cannot be causally connected. The light cone grows from that boundary. At any event along your world line, light sent outward spreads through space as time passes. In a simplified diagram with one spatial direction, its paths form two diagonal lines. Add the other spatial directions, and the expanding light forms a cone. The upper cone contains events that light or slower signals from the present event could reach. The lower cone contains events that could have sent light or slower signals to it. Outside those cones lie events too distant to connect with the event in time. This division is preserved for every observer. The angle of coordinate axes may change. The line each observer calls simultaneous may tilt. Measured distances and coordinate durations may differ. But the light cone remains the boundary of possible influence. This gives spacetime a structure that is both flexible and firm. The division into universal moments is flexible, because different observers slice the events differently. Causal accessibility is firm because every observer agrees about which events lie inside, outside, or on the light cone. The geometry does not tell one observer that light can reach an event while telling another that it cannot. All valid descriptions preserve that distinction. So when space and time mix, they do not dissolve into an arbitrary blur. They mix according to precise rules. Some properties change with the frame. Some survive every change of frame. The interval survives. Proper time survives. The causal character of the separation survives. This is enough for observers moving differently to describe one shared reality. Imagine two events inside your future light cone. One might be the next tick of the clock beside you. Another might be a signal reaching a detector across the room. You could travel from the present event to either of them without exceeding the speed of light. Their separation is time-like if a slower-than-light object can connect them, or light-like if only light can do so. Events outside the cone are space-like separated. No object or signal moving at or below the speed of light can connect them from the present event. These three kinds of separation are more fundamental than a universal classification into past, present, and future across the whole cosmos. Past and future remain unambiguous within the light cones. Outside them, distant order depends on the observer. The geometry keeps exactly the amount of temporal order needed for physical influence, but it does not add a master sequence where no influence can pass. That is a more economical universe than the one imagined by absolute time. It does not carry an invisible clock reading at every point, synchronized from outside the system. Instead, local clocks follow world lines, light defines the connecting structure, and invariant intervals allow every observer to translate their measurements into every other observer's description. This framework also explains why no experiment performed inside a smoothly moving laboratory reveals an absolute motion. If a spacecraft drifts at constant velocity with its windows covered, every local law of physics behaves normally. Light crosses the cabin at the same measured speed in every direction. Clocks and rulers behave as expected in that frame. There is no hidden wind passing through the ship to reveal motion through absolute space. The traveler can call the spacecraft at rest. An observer on Earth can call Earth at rest. Neither statement is complete without naming the reference frame, and neither is physically privileged by uniform motion alone. What both observers share is the spacetime interval between events. That is where the common reality lives in the mathematics. Not in one universal set of distances. Not in one universal set of clock readings. In the relationships that remain unchanged when the description changes. There is a quiet consequence hidden in this. The shape measured by a clock is not located somewhere behind the events, like a rigid container holding them. It is expressed through the relationships among the events themselves. A world line has proper time because of how its neighboring events are separated in space-time. A light cone has its form because of which events can exchange signals. Motion changes the coordinate description, but the invariant relationships remain available to every observer. This is why a clock can reveal geometry without seeing the whole universe. It only has to follow its local path. Tick by tick, the clock accumulates proper time. It does not need to know how another observer labels the surrounding events. It does not need access to a cosmic clock or an external map. Its reading is the space-time length of its own history. A clock beside another clock along the same path accumulates the same duration. A clock that leaves and returns can accumulate another. When they meet, the comparison reveals that their histories had different geometric lengths. The clocks have turned geometry into a physical record. So we return to the question of the missing universal present, though it now has a different shape. The problem is no longer only that observers disagree about which distant events are happening now. We can see why they disagree. Each observer divides the same invariant spacetime into different amounts of space and time. The shared structure lies beneath those divisions. A distant present depends on the observer. The interval between events does not. A clock's coordinate rate depends on the frame used to describe it. The proper time carried along its world line does not. This is the balance that special relativity creates. It gives up absolute space and absolute time, but it does not give up measurement, prediction, or a common physical world. It replaces the old background with spacetime geometry. For now, that geometry has been flat. We have imagined empty regions, steady motion, straight world lines, and light traveling without being deflected. The clocks disagreed because of their different paths and velocities, not because space contained planets, stars, or gravity. The real universe is not empty. Earth bends the paths of falling objects. The sun holds planets in orbit. Stars gather into galaxies. Near black holes, the relationship between clocks can become extreme. Einstein's next step was to stop treating gravity as a force acting inside the space-time geometry and ask whether gravity might be part of the geometry itself. If that is true, a clock's rate can change even when the clock is not racing through space. Two clocks can remain at rest relative to each other, separated only by height, and still accumulate different amounts of time. The shape behind every clock is about to become curved. So far, we have imagined clocks moving through empty space-time where no planet, star, or other source of gravity disturbed their paths. In that simplified setting, two clocks could accumulate different durations because they moved differently. One remained on a direct world line, while the other traveled outward and returned. But motion is only one way for clocks to disagree. Place one clock on the floor and another on a shelf above it. Keep both clocks still relative to the room. Let them remain there for a long time, with no spacecraft, no high speed, and no journey through the solar system. The clock on the shelf will accumulate slightly more time. The difference is extremely small across the height of an ordinary room, but it is physical. With sufficiently precise optical clocks, researchers can measure changes in clock rate over height differences much smaller than a person. The upper clock ticks faster because it lies higher in Earth's gravitational field. This effect is often called gravitational time dilation. The phrase can make it sound as though gravity reaches into a clock and slows its mechanism, but the mechanism is not the important part. Replace the optical clock with another kind of clock, and the same relationship remains. Atomic transitions, chemical reactions, biological processes, and every other local process follow the proper time along their path. The lower clock does not malfunction. Its atoms behave normally. Each local second feels like a complete second. If you lived beside that clock, your breathing and thoughts would remain synchronized with it. You would not notice your own time changing. The difference appears only when the lower clock is compared with a clock following another path through the gravitational field. On Earth, the effect is gentle. Raise a clock by 1 meter, and it gains only a tiny fraction of a second per day, relative to the clock below. A human lifetime is too short, and the human body is too imprecise to sense the difference directly. Modern atomic clocks can detect it because their internal frequencies are stable enough for tiny changes to become measurable. Gravity, therefore, changes the comparison between clocks, even when the clocks are not moving relative to each other. That result required a new understanding of gravity. In Newton's description, gravity is a force acting across space. Earth pulls an apple downward. The sun pulls Earth into an orbit. Space and time remain the background in which those forces operate. Einstein approached the problem from another direction. Imagine that you are inside a sealed room with no windows. The room may be standing on Earth, where the floor pushes upward against your feet. Or it may be inside a rocket far from every star and planet, with its engines accelerating the room upward through empty space. From inside, the two situations can appear remarkably similar. Release an object in the room on Earth, and it falls toward the floor. Release an object in the accelerating rocket, and the floor rises to meet it. A beam of light sent horizontally across the rocket also behaves in an interesting way. While the light crosses the cabin, the rocket accelerates upward. The opposite wall rises before the beam reaches it, so the light strikes a point slightly lower than where it was aimed. To someone inside, the light follows a curved path downward. If acceleration and gravity are locally equivalent, then light should also bend in a gravitational field. And if light changes its path, the network of clocks used to measure that light cannot remain untouched. Imagine a tall accelerating rocket with one observer near the floor and another near the ceiling. The lower observer sends a pulse of light upward once every second according to the lower clock. During the journey of each pulse, the rocket continues accelerating. The upper observer moves faster before each pulse arrives than when it was emitted. The spacing between the arriving pulses changes. The upper observer receives them at a different frequency from the frequency measured at the floor. Since the pulses can be used as clock ticks, the observers conclude that their clocks are running at different rates. Through the equivalence between acceleration and gravity, the same reasoning applies to a stationary tower on Earth. A clock higher in the tower accumulates more time than a clock lower down. This is not an extra adjustment placed on top of space-time. It tells us that the spacetime geometry itself is different near matter and energy. The straight world lines of special relativity are no longer globally straight in the old sense. Light still follows the most direct paths available to it, but the geometry through which those paths run is curved. An object released above Earth follows one of those paths. From the ground, it appears to accelerate downward. In general relativity, the freely falling object is not being pulled away from its natural motion by an invisible force. It is following a natural path through curved spacetime. The ground beneath it behaves differently. Earth's surface prevents the ground, the building, and your body from following free-fall paths toward the planet's center. The floor pushes upward against you. That pressure is what you feel as weight. A person falling freely feels weightless, because nothing is preventing their body from following its local spacetime path. For a short time and over a small region, the falling person can treat gravity as absent. Objects released beside them float nearby. Light behaves almost as it would in an inertial spacecraft. But this removal of gravity works only locally. Make the falling room large enough, and small differences appear. Objects released on opposite sides do not remain perfectly parallel because both move toward Earth's center. The gravitational field varies from one location to another. These variations are tidal effects. They reveal that gravity cannot be removed everywhere by choosing a freely falling frame. The curvature remains in the relationships between neighboring paths. Spacetime can look flat within a sufficiently small region, much as Earth's surface looks flat across a quiet room. Extend the region far enough, and the hidden curvature becomes measurable. Clocks are among the instruments that reveal it. Place clocks at different heights, and their rates differ. Move clocks along different routes through a gravitational field, and their final readings depend on those routes. Send clocks into orbit, and both velocity and gravitational position affect their accumulated time. Satellites used for navigation carry atomic clocks, while ground systems monitor and adjust the timing information needed to calculate positions. Their clocks operate higher in Earth's gravitational field and move rapidly relative to clocks on the surface, so practical navigation requires relativistic clock modeling rather than one universal rate shared by orbit and ground. The phone that locates itself beneath an open sky therefore depends on a universe in which clocks do not all tick together. The corrections are not philosophical. Without accurate timing, a receiver cannot infer its distance from the satellites transmitting signals. A small timing error becomes a much larger positioning error because the signals travel at the speed of light. Relativity is built into the timing architecture. If you are enjoying this quiet journey through time and space-time, subscribing is a simple way to find the next one when you are ready. Now let the gravitational field become stronger. Imagine a clock lowered slowly toward a very dense object. The clock continues to tick normally beside itself. Nothing inside it announces that its local seconds are changing, but an observer remaining farther away compares the lower clock with a clock at the higher position and finds that the lower one accumulates less time. Signals sent upward from the lower clock arrive, with a reduced frequency. The distant observer measures the arriving signal at a lower frequency than the signal measured beside the clock. The light is gravitationally redshifted. The shift in light and the difference between clock rates are two descriptions of the same relationship. Near Earth, the difference remains small. Near a neutron star, it becomes much larger. A neutron star can contain more mass than the Sun compressed into a sphere only tens of kilometers across. A clock near its surface would accumulate time more slowly relative to a distant clock than a clock near Earth. The local observer would still feel each second normally. The distant comparison would reveal the difference. Continue toward a black hole, and the relationship becomes more extreme. A black hole is not simply an object with an unusually strong force surrounding it. It is a region where the geometry of space-time has formed an event horizon, a boundary beyond which future directed paths cannot return to the distant exterior. Light emitted just outside the horizon can still escape, but it loses frequency as it climbs outward. Pulses sent from a descending clock arrive farther and farther apart for a distant observer. The clock appears to slow. Its light reddens. Its image fades. In the standard description of a distant stationary observer, the falling clock never appears to cross the horizon within a finite amount of that observer's coordinate time. The final signals become increasingly delayed and increasingly faint. But the falling clock does not experience an infinite wait at the horizon. If the black hole is large enough and tidal forces there are not immediately destructive, the clock can cross the horizon after a finite amount of its own proper time. Nothing local must mark the crossing with a sudden wall or flash. The two descriptions refer to different time coordinates. The distant observer uses a time adapted to remaining outside the black hole. The falling clock carries its own proper time along a path that continues inward. This does not produce two incompatible realities. Both descriptions can be translated within the geometry. They agree about signals that are sent and received, about the clock's local readings, and about the fact that no signal emitted after crossing the horizon reaches the distant exterior. The horizon shows how far the idea's shared present can fail. Outside the black hole, observers may choose many ways to divide spacetime into surfaces of equal time. Inside, every future-directed path leads farther inward, just as every ordinary future-directed path leads toward later events. The direction toward the center begins to behave less like an optional spatial direction. You cannot remain at a fixed radius inside the horizon in the way you can remain at a fixed location in an ordinary room. Moving toward smaller radius becomes part of moving toward the future. This is not because space has simply turned into time in a literal exchange of labels. The geometry has changed which directions correspond to physically possible future paths. The light cones have tilted. Far from the black hole, a light cone allows signals to move inward or outward. Closer to the horizon, the outward side narrows relative to the distant coordinates. At the horizon, the future light cone no longer contains a path that leads back to the exterior. Inside, even light-directed outward moves toward a smaller radius. The horizon is therefore defined by causal geometry. It is the boundary between events whose future signals can reach distant space and events whose future signals cannot. A distant observer may speak of the edge of the black hole as though it were a place. It is also a statement about time. It separates two kinds of future. The first still contains routes to the exterior universe. The second does not. This connection between gravity, clocks, and causal paths appears throughout general relativity. Matter and energy affect spacetime geometry. The geometry determines how clocks accumulate time and how freely moving objects follow their paths. Those objects and fields contribute to the matter and energy that shape the geometry. The relationship is not a simple force passing across a fixed stage. The stage and the motion upon it cannot be separated so cleanly. Even so, spacetime does not behave like a material sheet that literally bends into some higher surrounding space. The curved rubber sheet image can help show why paths converge, but it also introduces a misleading outside viewpoint. A rubber sheet bends because it sits inside a larger space and is pulled downward by gravity. Spacetime curvature requires no external room and no second gravity pulling it into shape. The curvature is measured from within. Carry a clock around a route. Send light along neighboring paths. Release objects and watch whether their trajectories converge. Measure the angles of a large triangle. Compare the circumference of a region with its radius. These internal relationships reveal whether the geometry is flat or curved. No observer needs to step outside the universe to see what it is bending into. A person living on the surface of a sphere can discover that the surface is curved without leaving it. They can travel in straight directions, compare paths, and measure triangles. Spacetime curvature is more complicated because it includes temporal relationships, but the principle is similar. The geometry announces itself through measurement. A clock at the bottom of a tower and a clock at the top follow different histories through that geometry. Their separation may remain constant. Their velocities relative to the tower may remain nearly zero. Still, their world lines contain different amounts of proper time. Height has entered the comparison of duration. Space and time are now joined not only by motion but by gravity. This gives the phrase "happening now" another complication. In curved spacetime, there may be no single global system of clocks that covers the whole universe with one natural time coordinate. Different coordinate choices can divide the same curved spacetime in different ways, and some spacetimes do not provide the simple global structure our everyday language assumes. Locally, the clock remains reliable. It records its own proper time. Nearby clocks can be compared. Signals can be exchanged. Experiments can be repeated. The difficulty appears when one local time is extended across large regions where gravity varies, matter moves, and spacetime itself evolves. A universal present was already absent in special relativity. Curvature does not restore it. It makes the search for one global clock even less natural. And this leads toward the question that has been waiting beneath the discussion. If the universe does not possess one present shared by every place, perhaps all events belong to a four-dimensional space-time without any objective boundary called now. Your birth, this moment, and events you have not yet experienced might then occupy different locations in one larger geometry. But that conclusion does not follow as simply as it first appears. Relativity constrains how time can be described. It does not by itself settle every philosophical question about what exists. So the next section will leave the clocks behind for a while and ask what their disagreement really means. Does the future already exist, or have we mistaken a mathematical map for the world it describes? The question appears naturally once spacetime is treated as a four-dimensional geometry. A map of a country contains cities you have already visited, the city where you are now, and cities you may visit later. They occupy different locations on the same map. Your journey through them does not bring the places into existence. It only changes which part of the map you are passing through. Space-time can invite a similar picture. Your birth is one event. This quiet moment is another. Tomorrow morning would be another event farther along your world line. The events can be represented together inside one four-dimensional structure, just as different places can appear together on a spatial map. From that representation, it is tempting to conclude that the future is already there. You have not reached it, but it exists in the same way that a distant city exists before you arrive. This view is often called eternalism. According to eternalism, past, present, and future events all belong to reality. The difference between them does not concern whether they exist. It concerns where they lie relative to an observer and which events the observer has experienced. Your present would then be local rather than cosmic. You occupy one region of your world line. Other events lie in the direction you call the past or the future. The feeling that reality is being created moment by moment would arise from the way conscious beings move through, remember, and process events within the larger structure. This picture fits comfortably with relativity in one important respect. Relativity does not provide one universal present separating what already exists from what does not yet exist. If existence were confined to the present alone, we would need to know which present. The platform observer and the train passenger divide distant events differently. One observer's present includes events that another assigns to the past or future. If only present events exist, then two observers in relative motion appear to disagree not merely about coordinates, but about which distant events are real. That seems difficult. The observer on the platform may say that a particular event near a distant star exists now. The passenger may say that the same event lies in the future, while another event at the star belongs to the present. If reality itself consists only of the present, the two descriptions seem to assign existence to different events. Eternalism avoids that problem. All of the events exist within spacetime, so different observers can select different cross-sections without causing reality to appear or disappear at a distance. Their presence differ. The larger structure does not. This is one reason the block universe is often associated with relativity. The phrase block universe describes spacetime as a complete four-dimensional structure. Nothing moves through it from an external viewpoint because there is no external time in which the whole structure could move. Change exists inside the block as differences between events. A seed is intact at one event. A shoot emerges at another. A tree stands at a later event. The tree changes because these stages occur in a definite order along its world line. The block does not need to change as a whole for change to exist within it. A road can contain a forest, a bridge, and a desert at different locations without the road itself turning from forest into bridge and then desert. A traveler encounters those regions in sequence. The block universe picture treats temporal change in a related way. Different states occupy different places in spacetime, and an observer encounters them along a world line. But the analogy can quietly smuggle in more than physics has established. A road is spatial, and the traveler already exists inside time while moving along it. If time itself is being explained, we cannot simply imagine another hidden time in which consciousness travels through the block. What would be moving? What would measure the speed of that movement? If the present advances 1 second every second, the explanation has only repeated the original mystery. It has placed time inside another time. Eternalism therefore tends to describe your world line without adding a separate moving present. Your experience at one event contains memories of earlier events but not later ones. At another event, your physical state contains a larger set of memories. The succession is written into the relations among those states. From inside the sequence, it feels as though the present moves. From the block description, there are simply different observer states at different events, each locally experiencing its own now. That may be logically tidy. It may also feel completely unlike life. The past does not feel distant in the same way that another city feels distant. It feels gone. The future does not feel like an unvisited place. It feels open. You can remember yesterday, regret it, and find records that it occurred. Tomorrow seems capable of developing in several ways, depending on decisions, accidents, and processes that have not finished. This asymmetry gives rise to another view. Presentism says that only the present exists. The past existed but no longer does. The future will exist but does not exist yet. Reality is concentrated in the current moment, and the passage of time is the continual replacement of one present by another. This is close to how experience first appears. A sound exists while it is being heard and then fades. A flame burns now, though yesterday's shape of the flame is no longer anywhere. You can preserve a photograph of an earlier event, but the photograph is present. The event it records is absent. Presentism keeps that distinction fundamental. The difficulty is extending the present across space-time. Locally, there is no problem. You are here now. The next tick of the nearby clock has not yet occurred for you. The previous tick has already occurred. Along your world line, the distinction between earlier, current, and later events remains clear. The trouble returns when presentism tries to describe distant existence. Which events near a distant galaxy exist at the same moment as the event you are living through? Relativity offers many valid answers, depending on the observer's motion. A presentist can respond in several ways. Perhaps one reference frame is secretly privileged, even though the known laws of relativity do not reveal it through ordinary uniform motion. There might be one true present beneath the descriptions, inaccessible or difficult to detect. That possibility can be proposed, but it adds structure beyond what special relativity requires. Another response is to make existence local. Only the local present is immediate, while questions about distant existence are treated more carefully. Yet a purely local present becomes difficult to combine into one account of a universe containing many separated observers. A third approach tries to define a preferred cosmic time using the large-scale structure of our universe. Cosmology sometimes uses a time coordinate associated with observers moving with the average expansion of matter. In a sufficiently smooth model of the cosmos, this produces useful surfaces of equal cosmic time. These surfaces help cosmologists describe the age and evolution of the universe. But usefulness does not automatically make them metaphysically unique. The cosmic time arises from particular features of the universe and the matter distributed through it. It is not the universal absolute time that special relativity removed from fundamental local physics. In regions with strong curvature, complex motion, or different global structure, a simple cosmic slicing may not exist or may not carry the same meaning. Presentism can therefore be maintained, but relativity makes it carry additional commitments. The theory does not make the view impossible with one quick argument. It removes the easy version in which the present is simply obvious and shared by all observers. Between presentism and eternalism lies another family of pictures. The growing block view says that the past and present exist, while the future does not yet exist. Reality forms a four-dimensional structure, but the structure is incomplete at its future edge. New events are continually added as time passes. This preserves the reality of the past. Your childhood is not merely nothing. It remains part of the growing history of the universe, even though you no longer occupy it. The future remains open because those events have not yet joined the block. The present is the advancing boundary where new reality appears. The idea combines features of ordinary experience with features of spacetime geometry. But it inherits the same question. Where is the boundary? If distant simultaneity depends on the observer, different observers disagree about the shape of the edge. One person's present boundary may pass through events another assigns to the already existing past or the not yet existing future. A growing block needs some rule that identifies one objective growth surface. Relativity does not provide an obvious universal choice. There is also a quieter problem. How could an observer know they are on the growing edge? Every event contains records of earlier events and no records of later ones. A person located in what we call the past would experience their own moment as present. They would also believe they were standing at the boundary of becoming. If the past remains real inside the block, those observers and their beliefs remain real too. From within any event, the local evidence looks similar. This does not automatically disprove the growing block view, but it makes the present boundary difficult to identify from inside space-time. There are other proposals. Some treat the passage of time as a real feature not captured completely by the geometric description. Some argue that becoming occurs locally rather than across one universal surface. Some preserve an objective present through additional physical structure. Others say that the question of which events truly exist may be asking the mathematical theory to answer something outside its purpose. Relativity predicts clock readings, signal paths, causal relations, and the behavior of matter with remarkable precision. It does not contain a line declaring that the future exists. A spacetime model represents events using 4 coordinates. From that fact alone, it does not follow that temporal coordinates must be interpreted exactly like spatial ones in every philosophical respect. A map can represent a possible route without proving that every event on the route has already occurred. A weather model can include tomorrow without making tomorrow present. But spacetime diagrams are not merely forecasts. They often represent complete solutions to physical equations, including events labeled earlier and later. The mathematics can treat the whole history as one object. The question is what kind of existence should be attributed to that object. Physics alone may not close the debate, because the positions can agree on the observable predictions, while disagreeing about the meaning of the structure producing them. An eternalist and a presentist can calculate the same clock readings. They can agree on gravitational time dilation. They can agree on the arrival of light signals and the behavior of particles. Their disagreement appears when they ask what exists beyond the events currently experienced. If no experiment distinguishes the interpretations, the argument cannot be settled by measurement alone, at least not in its simplest form. This does not make the question empty. The interpretation changes how we understand possibility, change, memory, choice, and the place of conscious experience within physics. But it asks for care. Relativity clearly tells us that distant simultaneity is not absolute. It tells us that clocks measure proper time along world lines. It tells us that space-time geometry can be represented as a 4-dimensional structure. The step from those statements to a fully existing future is an interpretation. Though it is an interpretation many find natural. The step from experience to a single universal moving present is also an interpretation, and relativity makes that one harder to state cleanly. Perhaps the safest place to pause is local experience. At this event on your world line, the future is not available to you. You cannot remember it. You cannot receive a signal from an event outside your past light cone. You cannot step into tomorrow by choosing a direction in the room. Your available actions depend on present physical conditions, and their consequences lie along future-directed paths. Whether those future events already exist in a larger space-time description does not allow you to inspect them. The block universe, even if correct, is not a book you can open to the final page. Information still travels through causal channels. Knowledge remains local. Uncertainty remains physical for observers who do not possess future data. The future can be fixed in one philosophical interpretation and still remain unknowable from your present event. It can be open in another interpretation, while the same physical probabilities and constraints apply. The experience of decision does not disappear merely because a complete space-time can be imagined. Your decision is itself an event within the history. Your reasons, uncertainty, and physical deliberation are part of the conditions producing what comes next. A block description does not replace those processes, it includes them. This is important because the phrase already exists can suggest that events occur without causes, choices, or development. But an eternalist universe still contains every conversation, hesitation, collision, biological process, and chain of reasoning that links earlier conditions to later results. The whole history may be represented together. Inside that history, events still happen because of other events. The complete map does not remove the roads. Still, one question remains untouched. Even if all events belong to space-time, why do they not feel equally present? Why do you remember one direction and anticipate the other? Why do broken objects remain broken while scattered heat does not spontaneously gather itself back into a flame? Why does the universe contain records of what we call the past, but not records of what we call the future? Relativity changes the geometry of time, but geometry alone does not explain its direction. The equations allow clocks to trace paths and observers to disagree about distant simultaneity. They do not, by themselves, explain why experience seems to flow from earlier states toward later ones. The distinction may not come from spacetime's basic coordinate structure. It may come from the physical contents of spacetime and the unusual condition in which the universe began. To understand the moving quality of time, we have to leave the debate over which moments exist and look at what actually happens inside those moments. Heat spreads. Structures decay. Records accumulate. Memories form in one direction. The arrow of time may not be written into every microscopic law. It may emerge from the way physical states are arranged, and from the fact that the universe appears to have begun in an extraordinarily ordered condition. A glass falls from a table and breaks across the floor. If a camera records the scene, the direction of the film is easy to recognize. In one direction, the glass begins as a single object, tips over the edge, strikes the floor, and scatters into many pieces. In the other, fragments slide together from different parts of the room, lift themselves from the floor, join without a seam, and settle gently on the table. The second film is not difficult to understand. It is simply unlike anything we expect to see. Nothing in the motion of one fragment seems impossible by itself. A piece of glass can slide across a floor. It can rise if something gives it enough momentum. Two fragments can collide. At the level of individual particles, many of the equations used to describe motion work almost as well when the direction of time is reversed. If every molecule in the room could have its motion reversed with perfect accuracy, the scattered fragments might retrace the paths that produced them. Vibrations in the floor would converge on the point of impact. Sound waves spreading through the air would return to the glass. Heat released during the collision would gather into the fracture lines. The pieces would meet with exactly the right positions and velocities. The glass would rebuild itself. The problem is not that the reversed motion violates a simple mechanical rule. The problem is arranging an enormous number of details with impossible precision. When the glass breaks, energy spreads into the room through microscopic channels. Molecules in the air move differently. The floor vibrates. The fragments rotate, bounce, scrape, and warm slightly. Light scatters from new surfaces. Every interaction passes part of the event into a larger environment. To reverse the process, all of those changes would have to cooperate. The air molecules would need to return with the right velocities. The vibrations in the floor would need to converge in the right pattern. The heat would need to concentrate at the correct places. Every fragment would need to arrive at the correct angle and speed. A tiny error would grow. One molecule moving in the wrong direction could disturb another. That disturbance could spread through more collisions until the returning fragments no longer met correctly. The forward process tolerates almost any microscopic detail. The reverse process tolerates almost none. This difference is where entropy enters. Entropy is often described as disorder, but that word can be misleading. A room may look untidy without having a useful thermodynamic meaning. A crystal may look highly ordered while its surrounding environment contains many possible microscopic states. A more careful description begins with the difference between a macrostate and a microstate. A macrostate is the broad condition we can observe and describe. A glass is intact on the table. Gas fills a box evenly. One side of a metal bar is hot and the other is cold. A microstate specifies the underlying physical details. It includes the positions, motions, and other relevant properties of the particles making up the system. Many different microstates can look like the same macrostate. There are many ways for air molecules to be distributed almost evenly through a room. The molecules can exchange places, directions, and speeds, while the air continues to look uniform. There are far fewer ways for all of the air molecules to gather by chance into one corner. Both arrangements are allowed by the basic mechanics, but the evenly spread arrangement corresponds to vastly more possible microstates. Entropy measures this multiplicity. A high-entropy macrostate can be realized by an enormous number of microscopic arrangements. A lower entropy macrostate occupies a much smaller region among all the possibilities. This is why a gas released into an empty container spreads out. At first, the gas occupies one side. The molecules collide with one another and with the walls. There is no tiny force instructing them to seek disorder. They simply move according to the local laws. But almost every available evolution carries the gas toward macrostates, in which it is more widely distributed, because there are so many more microscopic ways for it to be spread out than confined. The reverse is not forbidden. The molecules could all happen to move toward one side at the same time. The probability becomes so small for a macroscopic gas that waiting for it is not a practical experiment. The number of particles is too large, and the set of arrangements producing the reversal is too narrow. The second law of thermodynamics summarizes this statistical tendency. For an isolated macroscopic system, entropy is overwhelmingly likely to increase or remain near its maximum. This is not the same kind of statement as saying that light travels at a fixed speed in vacuum. A rare fluctuation can locally reduce entropy. In small systems, fluctuations can be observed and measured. but as the number of interacting particles grows, large sustained reversals become extraordinarily unlikely. The world around you contains numbers of particles far beyond ordinary imagination. A sip of water contains an immense population of molecules. A breath of air contains far more interacting components than any person could track. A warm object exchanges energy with its surroundings through collisions and emissions. When all of those components are considered together, the statistical direction becomes dependable. Heat flows from a warmer object into a cooler one. Perfume spreads through a room. Cream mixes into coffee. A flame consumes fuel and releases heat. A body ages as biological structures undergo chemical change. These processes define the thermodynamic arrow of time. They distinguish one temporal direction from the other, even when many underlying microscopic laws do not strongly distinguish them. Experimental work in both classical and quantum systems connects the observable direction of irreversible processes with positive entropy production. But entropy increase alone does not yet explain why the direction points from what we call the past toward what we call the future. Suppose you are given a box of gas in a state of unusually low entropy. If you allow the system to evolve without knowing how it reached that state, statistical reasoning predicts that entropy will increase away from the low entropy condition. That prediction can work in either temporal direction. Starting from the special state in the middle, typical microscopic evolutions lead toward higher entropy on both sides. This reveals something easy to overlook. The laws in the current state are not always enough to explain one arrow. We also need a boundary condition. The world contains an abundance of lower entropy conditions behind us and higher entropy conditions ahead of us. A broken glass was once intact. A cooled cup of tea was once warm. A human body developed from a smaller and more ordered biological history. We do not usually encounter systems whose entropy decreases toward the future because they were carefully arranged by conditions lying in that future. The asymmetry appears to reach far beyond any single room or object. It leads back through the history of Earth, through the formation of the solar system, and into the early universe. The early universe was hot, dense, and remarkably smooth on large scales. Calling that state low in entropy may sound contradictory. A hot gas in a box is usually closer to equilibrium than a cool, uneven gas, but gravity changes the comparison. For matter interacting through gravity, a smooth distribution is not the final equilibrium state. Gravity encourages matter to clump. Small variations grow as gas gathers into clouds, clouds collapse into stars, stars collect into galaxies, dense objects form, and black holes come to carry enormous entropy. A smooth early universe, therefore, had a special gravitational condition. Matter had not yet developed the clumped structures that gravity would later produce. As the universe expanded, gravity amplified small irregularities. Stars and galaxies formed. Nuclear reactions inside stars created new elements and released energy. That energy spread into colder surroundings, allowing local structures to grow while total entropy increased. Life on Earth participates in this same process. A living organism does not violate the second law by becoming organized. It takes in relatively concentrated energy and low entropy resources, uses them to maintain internal structure, and releases heat and waste into the environment. The organism can become locally more ordered because the wider system gains entropy. The sun provides a continuing flow of energy in a useful form. Earth absorbs sunlight from a hot source and radiates energy back into colder space. Within that flow, weather systems move, oceans circulate, plants grow, nervous systems develop, and memories are formed. The local complexity around you rests inside a larger increase of entropy. This is why the arrow of time can appear in many different forms while still pointing in the same direction. There is a thermodynamic arrow seen when heat spreads and entropy rises. There is a radiative arrow seen when waves move outward from sources rather than arriving from every direction in a perfectly coordinated collapse. There is a biological arrow seen in development, aging, healing, and decay. There is a psychological arrow seen in the difference between remembering and anticipating. These arrows are not necessarily separate laws. They may be different consequences of the same low entropy boundary behind us. A stone dropped into still water creates expanding ripples. The time-reversed scene would show ripples arriving from every part of the pond, converging on one point and lifting the stone into a waiting hand. The local equations can describe the converging waves. What makes them unusual is the required preparation. Every section of the water would need the correct motion before the stone rose. The pond would already contain a carefully coordinated record of the future event. Ordinary conditions are not arranged that way. We prepare stones above water. We do not prepare entire ponds with incoming waves precise enough to launch them. The distinction lies in the boundary conditions surrounding the event. This also explains why reverse film can look wrong even when no single movement is impossible. Smoke gathers into a candle. Ash becomes paper. Spilled water climbs into a glass. A footprint disappears as sand grains move into exactly their earlier positions. Every scene requires correlations spread through the environment. The later state must contain an extraordinary coordination capable of reconstructing the earlier one. Forward processes create correlations and records as they unfold. Reverse processes require those correlations to be waiting in advance. A glass that breaks leaves evidence. Fragments rest on the floor. Scratches appear at the point of impact. Sound reaches nearby ears. Light from the event travels outward. A camera may store changing electrical states. A brain may change as it forms a memory. All of these records are physical. They involve energy, matter, and correlations between systems. The glass does not merely break in isolation. Its history becomes distributed through the environment. This distribution makes the past accessible in a way the future is not. You can inspect the fragments and infer that a glass once existed. You can follow a crater and infer an impact. You can study starlight and reconstruct earlier stages of a star. You can read tree rings, sediment layers, genetic sequences, photographs, and written pages. The present contains traces of earlier conditions. It does not contain comparable traces of ordinary future conditions. That difference feels so natural that we rarely ask what makes it possible. Why should the present be correlated with the past more strongly than with the future? Why should a memory point backward? Why should records accumulate on only one side of an event? One answer is that producing a durable record normally increases entropy somewhere. A camera must change its internal state. A brain must alter connections and chemical conditions. A mark must be left on paper, stone, magnetic material, or some other physical system. The recording device begins in a condition capable of accepting information. After the interaction, its state becomes correlated with what happened. Preparing, maintaining, or resetting the device has a thermodynamic cost. The process fits naturally into a universe where usable free energy flows from lower entropy conditions toward higher entropy ones. The recording system does not sit outside physics. Memory is one of the things entropy makes possible. This should be stated carefully. Researchers still debate how completely the thermodynamic arrow explains every aspect of time's apparent direction. There are models in which arrows arise under different cosmological assumptions, and low entropy initial conditions remain part of an active foundational problem rather than a finished explanation. What is well established is the close relationship between macroscopic irreversibility, entropy production, and the special conditions needed to explain why the observed arrow points consistently in one direction. The low entropy past is sometimes called the past hypothesis. It is not a new force. It is a proposal about the boundary condition of the universe. The physical state at one end of the history was highly special, and ordinary statistical evolution away from that condition produces the direction we observe. This shifts the mystery. Why does time move forward? Physics may answer that no universal substance called time is moving. World lines contain ordered events, clocks accumulate proper time, and matter evolves from a special lower entropy boundary toward states available in far greater numbers. The feeling of passage may arise within physical systems following that direction. But then a deeper question appears. Why was the boundary special? If high entropy states occupy overwhelmingly more of the available possibilities, why did the observable universe begin in a condition from which entropy could rise for billions of years? Inflation does not automatically remove the question, because the conditions required for inflation and the entropy accounting of gravitating systems introduce their own difficulties. Some cosmological proposals attempt to generate arrows in more than one temporal direction or avoid a simple low entropy beginning. But no single account has settled the issue. For the moment, we do not need to solve the origin of the boundary. We only need to notice what it does. It gives physical processes a direction. It allows stars to shine by releasing concentrated energy. It allows temperature differences to perform work. It allows organisms to maintain themselves temporarily. It allows events to leave traces. and it gives a brain something it can call the past. Return once more to the broken glass. The fragments do not tell you where they will be tomorrow. They tell you something about where they came from. Their positions, shapes, and fracture lines contain correlations with an earlier intact object. Dust may have been displaced. The floor may carry marks. Someone nearby may carry a memory. The past event has been copied imperfectly into many present systems. The future has not. That difference may be closer to the experienced flow of time than any clock or coordinate. A clock tells you how much proper time lies along a path. Entropy helps explain why the path contains records facing one way. The present feels as though it moves because each new local state inherits traces of earlier states while lacking traces of later ones. A listener at this moment contains memories of the opening question, but not of the final sentence still ahead. The next section follows that asymmetry into the physical structure of memory itself. A memory is not a view into another time. It is a pattern existing now, produced by an interaction that occurred earlier, and maintained by a continuing flow of energy through matter. To understand why you can remember yesterday but not tomorrow, we have to ask how the past becomes a record inside the present. A memory is not a view into another time. It is a physical pattern that exists now. The conversation you had yesterday is not stored somewhere outside the present, waiting to be visited again. What remains is a changed condition inside your nervous system, along with whatever traces the conversation left in other places. A written message may still exist. A chair may have been moved. Another person may carry a related memory. Sound waves from the words have dispersed, but the event has altered systems that continue into the present. Memory is one of those alterations. This can feel disappointing at first. A remembered room may appear so complete that it seems as though the mind has reopened a window into the past. You can picture the color of the walls, the position of a face, or the sound of a familiar voice. Sometimes the scene arrives with enough detail to create the sensation of being there again. But the remembered image is being constructed now. Neurons are active now. Chemical conditions are changing now. Signals are moving through a living network now. The memory refers to an earlier event, but the act of remembering belongs entirely to the present moment. That is why memories can change. A stored record is not always a perfect copy. Each act of recall can combine old traces with current emotion, later knowledge, and details supplied by expectation. Two people can experience the same event and preserve different versions of it. A person can remember something confidently and still be wrong. The weakness of memory does not make it unreal. It makes memory physical. A physical record is shaped by the process that creates it, the material that carries it, and the conditions under which it is retrieved. A footprint depends on the softness of the ground. A photograph depends on the camera, the exposure, and the position of the lens. A fossil preserves some structures and loses others. A memory follows the same broad rule. The present contains an imperfect trace of an earlier interaction. This is enough to give experience a direction. You remember waking earlier today, but you do not remember waking tomorrow. You may imagine tomorrow morning, predict it, fear it, or look forward to it, but imagination and memory do not feel the same. A prediction remains uncertain. A memory arrives with the claim that something has already happened. That claim can be false, but the direction remains consistent. False memories still point toward what the mind treats as the past. They do not normally arrive as records of future events that later become their causes. The reason may seem obvious. Tomorrow has not happened yet, so there is nothing to remember. That answer works within ordinary experience, but it does not fully explain the physics. If a block universe interpretation is correct, future events may belong to spacetime just as past events do. Even then, an observer at the present event has records of one direction and not the other. The asymmetry remains. The geometry alone does not explain why a brain at one point on its world line contains information correlated with earlier points but not later ones. Entropy begins to fill that gap. To form a memory, a system must change. A camera sensor changes when light reaches it. A magnetic drive changes when information is written. Ink changes the surface of paper. A nervous system changes when an experience alters activity and connections within it. The recording system must begin in a condition capable of being changed in a controlled way. After the interaction, some part of its state becomes correlated with the event. A dark region in a photograph corresponds to less light-reaching part of the sensor. A groove in a surface corresponds to an object passing across it. A pattern of neural activity and altered connections may correspond to an experience. though the relation is far more complex than a simple image stored in one location. The record is useful because the present state carries information about an earlier state. But creating that correlation is not free. The recording device consumes energy, releases heat, or depends on a larger process that does. A camera uses a battery. A computer must be powered. A brain survives only through constant chemical activity, blood flow, temperature regulation, and the conversion of food into usable energy. Even when the energetic cost of one small memory is difficult to isolate, the system that forms and maintains memories operates inside a thermodynamic flow. It receives energy in a concentrated form. It uses that energy to preserve structure and perform work. It releases energy in a more dispersed form. Memory belongs to the same arrow as metabolism, heat flow, and the spreading of radiation. This is why the connection between entropy and memory is deeper than the simple claim that memories become disorganized over time. The important point is not merely that records decay. It is that records are formed by physical processes that inherit the low entropy conditions of the past and produce additional entropy as they operate. A brain can preserve information because it is not in equilibrium. It is a maintained structure, continuously exchanging matter and energy with its environment. When that flow ends, the organized activity required for memory eventually ends with it. The living observer therefore occupies a narrow thermodynamic condition, far from complete disorder, but sustained by processes that increase entropy outside the local structure. Within that condition, earlier events can leave organized traces. A sound changes the nervous system. Light changes the retina and the brain. An injury changes tissue. A repeated action changes skill. The observer carries these changes forward along a world line. The word forward matters because the traces are created after the interaction in the causal order. Light reaches the eye before the corresponding visual memory is formed. A conversation occurs before the later recollection. A detector is struck before its display changes. The cause enters through the past light cone. The resulting record persists into later events. A record of the future would require a different arrangement. The present system would need to be correlated with an event that has not sent any signal into it. Information would have to appear before the causal interaction that supposedly produced it. Relativity does not permit ordinary signals to travel from outside the future light cone into the present. The causal geometry already blocks one simple route to future memory. But causal order alone does not explain every aspect of the asymmetry. A present event could, in principle, contain a pattern that happens to match a later event by coincidence. The pattern would not be a genuine memory produced by that future event. It would be a prediction, a random correspondence, or part of a larger arrangement whose causes lie elsewhere. For it to function as a reliable record, the correlation would need a physical explanation. Past records have one. The earlier event interacted with the recording system. Future records do not have that ordinary causal history. This is why a photograph of yesterday carries evidential weight, while a painting of tomorrow does not. The photograph was physically exposed to light from the earlier scene. The painting may resemble what later happens, but the resemblance alone does not show that information traveled backward from the future. A record is more than similarity. It is a correlation produced by a causal process. The universe is filled with these backward-pointing correlations. Light arriving from a galaxy carries information about an earlier state of that galaxy. A crater carries information about an earlier impact. Radioactive products carry information about earlier decays. The distribution of elements in a star carries information about earlier nuclear processes. The cosmic background radiation carries information from an early stage of the universe, preserved in photons that have traveled ever since. Each trace exists now. Each was produced by events lying within its past. The present is therefore crowded with the past. Not with the past itself, but with physical descendants of earlier events. This gives experience its thickness. The present moment is never only what is happening locally at one instant. It also contains structures inherited from earlier moments. Your body carries the history of its development. The room carries marks left by earlier use. The planet carries layers formed by ancient oceans, impacts, eruptions, and living organisms. Even empty-looking space contains radiation that began its journey long before anyone was here to receive it. The future does not appear in the same way. There are plans, probabilities, trajectories, and constraints. A planet's orbit can be predicted. An unstable atom has a probability of decaying. A person may have an appointment written on a calendar. These are present structures that help describe what may happen later. They are not traces produced by the later event. The calendar entry was created by an earlier decision. The orbital prediction comes from present measurements and physical laws. The probability describes possible outcomes based on what is known now. They point toward the future without arriving from it. This distinction may help explain why the future feels open even in a world governed by precise laws. An observer never possesses the complete microscopic state of the universe. Information is limited by causal distance, measurement, quantum uncertainty, and the practical impossibility of tracking every relevant interaction. The future is approached through models. The past is approached through records. Both can be uncertain, but the uncertainty has a different shape. You may be unsure what happened in a room yesterday because the evidence is incomplete. You may be unsure what will happen in the room tomorrow because the event has not yet interacted with the present. In one case, the traces are damaged or missing. In the other, the ordinary traces have not been created. The mind turns this physical asymmetry into a psychological one. A memory is experienced as having happened. An expectation is experienced as not yet settled. A regret points backward because its object is represented by a record of an event that can no longer be influenced from the present. A hope points forward because its object lies among events that may still be reached by future-directed actions. The emotional arrow follows the causal arrow. You cannot send a decision into your past light cone and change an event already recorded there. You can act now and influence some events inside your future light cone. The range may be limited. Many future events are too distant, too constrained, or too far beyond your control. But the basic orientation remains. Action points toward one side of the present because causal influence does. Memory points toward the other because records arrive from there. This may be the closest physics comes to the feeling of standing inside a moving now. The present is the local region where records from earlier events are available, and actions toward later events are still being formed. Nothing needs to flow through the universe as a separate substance. The observer changes. The observer's records accumulate. The set of reachable future events changes as the world line advances. At one event, you remember fewer things. At a later event, you may remember the earlier one. The difference between those physical states produces the appearance of movement through time. Imagine a sequence of observers placed along one world line. Each is the same person at a different event. The earlier observer remembers childhood, but not the conversation that will happen tomorrow. The later observer remembers childhood and may also remember that conversation. Each experiences their own event as present. Each contains records pointing toward one direction along the world line. There is no additional observer floating above the sequence and sliding from one version to the next. The sequence itself contains the changing experience. This can be difficult to accept because experience feels unified. You do not feel like a collection of observer states arranged along a path. You feel like one continuing self moving through successive moments. That continuity is also carried by records. The present brain contains memories, habits, bodily structures, language, and expectations inherited from earlier states. The later self resembles the earlier self because information and matter have been passed forward through continuous physical processes. Identity is not recreated from nothing at each moment. It persists through causal connection. The person listening now is linked to the person who began listening because every intermediate state developed from the one before it. Memory helps the later state recognize that connection. But memory alone is not the whole of identity. People remain themselves through periods they do not remember, including sleep, anesthesia, infancy, or ordinary forgotten hours. Continuity is broader than conscious recall. It includes the ongoing world line of the body and the causal development of the system. The feeling of a self moving through time may therefore be another local expression of physical inheritance. Each state receives structure from earlier states and contributes structure to later ones. The direction of that inheritance follows the thermodynamic and causal arrows. This does not explain consciousness completely. It does not tell us why physical processing is accompanied by subjective experience, or why the present feels vivid while memory feels distant. Those remain open questions. But it narrows the mystery. The mind does not need access to a universal moving present to distinguish past from future. It lives inside a system where information arrives asymmetrically. The past leaves records. The future offers possibilities. The present is where those records and possibilities meet in one local physical state. Return to the clock beside you. Its latest reading is not more real than the previous one, because the display possesses a special substance called presentness. The previous reading altered the mechanism and was replaced by the next state. A camera could preserve both readings in a sequence of images. Your memory may preserve an impression of some of them. The clock measures proper time along its path. Your nervous system builds records along its own. Together, they create the familiar experience of duration passing in one direction. But the larger universe may not contain any master clock coordinating all of these local histories. General relativity already makes global time difficult. Quantum theory makes the problem more severe. When physicists try to describe the entire universe, rather than one system evolving against an external clock, the ordinary time variable can disappear from the deepest equations. That does not mean nothing happens. It may mean that time has been asked to play two roles that cannot both remain fundamental. The next step is to enter that problem slowly and ask whether time is a basic ingredient of reality, or a relationship that appears when one part of the universe is used to measure change in another. Imagine trying to describe every clock in the universe while using one more clock outside the universe to measure them. The extra clock would make the calculation easier. It could remain untouched while galaxies formed, particles interacted, and space-time changed. Its reading would provide a clean sequence. First, the universe would have one state, then another, then another. But there is no outside clock. The universe, by definition, includes every physical clock we can use. Any device that measures change is already part of the system being described. Its gears, atoms, light pulses, or chemical reactions must obey the same laws as everything else. This creates a problem that does not appear when we study a small system in a laboratory. In ordinary quantum mechanics, time usually enters as an external parameter. A wave function changes with time, and the equations tell us how the probabilities of different outcomes evolve as that time passes. The clock on the laboratory wall is not usually included in the quantum system. Neither is the building Earth or the wider universe supporting the experiment. They form the background against which the small system is described. A particle changes. An atom emits light. A detector records an outcome. The variable, called time, orders these changes from outside the mathematical description of the system itself. General relativity treats time differently. A clock is part of spacetime, and spacetime is influenced by matter and energy. The geometry is not a fixed background that remains unchanged while everything else evolves. It participates in the evolution. Clocks measure paths through that geometry. Matter affects the geometry. The geometry affects the motion of matter and the rates of clocks. This works well when gravity is described classically. It also works well when quantum mechanics describes particles and fields against a background spacetime. The difficulty appears when gravity itself must become quantum. Now, the geometry that normally tells us what space and time mean must enter a quantum description. The clock cannot remain outside the system because the clock depends on the geometry, and the geometry is one of the things being quantized. The background has joined the experiment. When physicists apply a canonical approach to quantizing general relativity, they encounter an equation associated with John Wheeler and Bryce DeWitt. Its appearance resembles part of quantum mechanics, but one familiar ingredient is missing. There is no external time variable telling the quantum state of the entire universe how to evolve. The equation can be written in a form that says the total state is constrained rather than advancing against an independent cosmic clock. This absence of explicit external time is one form of what physicists call the problem of time. Taken too literally, the result can make the universe sound frozen. If the fundamental state does not change with an outside time, how can anything happen? How can stars ignite, planets orbit, clocks tick, or a person grow older? The mistake may be expecting the universe as a whole to change in relation to something outside itself. A smaller system can change relative to a laboratory clock. The laboratory can change relative to Earth's rotation. Earth's rotation can be compared with atomic clocks and the motion of other astronomical bodies. Each comparison places one physical process beside another. But when the description expands to include everything, there may be no remaining external process, against which the complete universe changes. This does not mean that change disappears inside the universe. It means that change may need to be described through relationships among its parts. Imagine a sealed box containing two devices. The first device is simple and regular enough to be used as a clock. Perhaps it contains a particle moving through a sequence of distinguishable states. The second device is the system whose behavior you want to describe. From outside the box, you could watch both devices evolve with laboratory time. But suppose the box is all you have. You cannot consult anything beyond it. The only available method is to compare one part with the other. When the clock device shows one state, the second device tends to show one condition. When the clock reaches another state, the second device tends to show another. The sequence appears in the correlations. The clock is not measuring an invisible substance flowing through the box. It provides one changing pattern that can be used to organize another changing pattern. This is called relational time. Time in this view is not first supplied as a universal background. It appears when one physical variable is used to track change in another. The idea is already familiar in ordinary life. Long before precise clocks, people used the changing position of the sun to organize activity. The sun did not release units called hours into the world. Its position changed in a regular enough way to compare with shadows, hunger, work, and sleep. A pendulum clock does something similar with repeated swings. An atomic clock uses regular transitions associated with atoms. Even the most precise clock does not detect time directly. It counts a physical process. Relational approaches extend that ordinary fact into the foundations of physics. Perhaps every meaningful statement about time is ultimately a statement comparing physical quantities. The question would no longer be, what is the state of the universe at time t? It would become, what state does one part of the universe have when another part has this reading? This change in language is small, but it removes the need for a master clock outside the whole system. One proposal associated with Don Page and William Wooters shows how this can happen in quantum theory. The total quantum state can remain stationary in the relevant global description, while subsystems still display change relative to one another. One subsystem acts as a clock. When the rest of the system is described conditionally on different readings of that clock, an ordinary sequence of evolution can appear. From the outside, if an outside existed, the complete state would not need to pass through a series of global moments. From within, an observer using the internal clock would recover a history. The clock and the observed system are correlated, and those correlations provide the sequence called time. This proposal does not settle the problem of time. A useful clock must behave reliably. Real quantum clocks are imperfect. The way a system is divided into clock and remainder can matter. Different choices of internal time may work well only in certain regions or approximations. There is also a difference between showing how familiar time can appear in a model and proving that this is how time arises in the real universe. Still, the mechanism gives a concrete answer to the fear that a timeless global equation must describe a world in which nothing happens. A complete state can be stationary while relationships inside it contain change. Think of a musical score lying motionless on a table. The page does not play from beginning to end. Every note is present in the written pattern. Yet the relations among the notes define an order that a musician can follow. The universe is not literally a score, and no external musician is required. The comparison only shows how a static description can contain an internal sequence without the whole description moving through another time. A quantum state can contain correlations that function as histories for observers inside it. The observers themselves are part of those correlations. Their clocks, memories, instruments, and bodies all belong to the same physical description. This returns us to the arrow of time. A relational clock can order changes, but ordering alone does not explain why records accumulate in one direction. A pendulum can label successive states whether entropy rises or falls. The deeper asymmetry still depends on the physical conditions of the systems using the clock. Some proposals bring the state of the system and its thermodynamic properties closer to the definition of time itself. The thermal time hypothesis, associated with Alencons and Carlo Rovelli, explores the possibility that a physical flow identified as time can be derived from the statistical state of a system rather than imposed in advance. In this approach, the state helps determine the relevant time flow. The proposal is mathematically motivated and remains one candidate among several, not an established description of how time universally emerges. Even work developing the idea notes that its concrete physical reach is still limited. The important shift is broader than any one proposal. At the beginning of our journey, time seemed like a universal current. Every object existed inside it, and one present appeared to cross the cosmos from end to end. Special relativity removed the universal present. Different observers divided distant events into different sets of simultaneous moments. Proper time then became local. Each clock recorded the duration along its own world line. General relativity made the rates of clocks depend on curved spacetime. The geometry itself changed, so no rigid external clock could stand behind every region. Quantum gravity pushes the idea further. The deepest description may contain no independent time parameter resembling the clock on a laboratory wall. Time may appear only after one part of the universe is compared with another. This does not prove that time is unreal. A relationship can be physically real. Distance is a relationship between locations. Temperature describes collective behavior. A wave can be real, even though it is made from the coordinated motion of many parts. Something does not become imaginary merely because it emerges from a deeper structure. The distinction concerns which level is fundamental. Water has temperature, but an individual water molecule does not carry the temperature of the glass by itself. Temperature becomes meaningful when many microscopic motions are described together. Time may behave in a related way. At the level of ordinary objects, it is measured with extraordinary precision. Clocks disagree by amounts predicted by relativity while unstable particles decay, planets move and brains form memories, and nothing in daily physics requires us to deny temporal order. But at a deeper level, the universe may contain correlations, constraints, quantum states, and causal relationships without one independent clock standing over all of them. The familiar time of experience could emerge when a sufficiently stable process is used as a clock, when other processes become correlated with it, and when entropy allows records to accumulate in one direction. That possibility joins the ideas we have followed. Relativity explained why there is no universal now. Spacetime geometry explained why different paths contain different durations. Entropy explained why physical records point toward one side of those paths. Memory explained why the past is carried into the present. Relational time suggests why change can still be meaningful even when no master clock exists. The universe does not need to announce one official moment. Every local clock can measure its own path. Every observer can build a history from correlations available along that path. When observers meet, they can compare clocks and records. Their measurements may differ, but the differences obey physical rules. The absence of a master clock does not prevent agreement. It changes what agreement means. Observers do not agree by discovering a hidden universal time beneath their clocks. They agree by translating one local description into another and identifying the events where their paths connect. Perhaps time, then, is less like a river crossing the universe and more like the order found within physical relationships. But even that sentence should be held gently. No accepted theory of quantum gravity has yet given a final account of time. The Wheeler-DeWitt approach is not the only approach. Relational models and thermal time remain proposals. Other theories preserve time in different forms or rebuild it using different variables. The honest conclusion is not that physics has proved time does not exist. It is that the simple version of time has not survived. The universal present is gone. The master clock is unnecessary. What remains are local durations, causal order, physical records, and correlations between changing things. And beside you, perhaps only a short distance away, a small clock continues to tick. Its rhythm does not belong to the whole universe. It belongs to one quiet path through it. The final step is to return to that clock, to the room around it, and to the person listening beside it, because the loss of universal time does not make the present less meaningful. It makes this local moment the only kind of present nature ever actually gives you. The clock beside you continues to tick, although by now it may feel less like a piece of machinery and more like a companion following the same narrow road through space-time. Its numbers change in a regular sequence. 1 second appears, then another. The display may look as though it is reporting the time, as though somewhere beyond the room there is one enormous clock producing the same seconds for every star, planet, and observer. But the small clock is doing something more modest. It is counting change along its own path. It moves with the room, with the building, and with Earth as the planet turns beneath the sky. Earth carries it around the sun. The sun carries it through the Milky Way, and the galaxy moves among other galaxies through an expanding universe. There is no fixed stage beneath all of that motion. There is no place where the clock could stop moving completely and reveal the true rate of time. Still, the clock works. Its local rhythm remains stable enough to organize a life. It can tell you when morning arrives, when a train leaves, when food has been cooking long enough, or how many hours have passed since the room became dark. It does not need the time of the universe to do any of this. It needs only a repeatable process and a path through spacetime. Your body keeps a different kind of clock. Its rhythm is less precise, but it is older than any device in the room. During the day, chemical cycles change as temperature rises and falls, hormones shift, hunger returns, and fatigue gathers slowly, sometimes long before you notice it. These processes are not synchronized perfectly with the display nearby. A minute can feel long while you wait for something painful to end. An hour can disappear while your attention is absorbed. A night of restless thought can feel larger than the daylight that follows it. The clock counts duration. The mind experiences it. Those two measurements belong to the same physical world, but they are not the same kind of record. A mechanical or atomic clock follows regular changes chosen because they can be counted reliably. Experience is built from memory, attention, emotion, prediction, and the changing state of a living body. This is why the present can feel wide or narrow. A sudden event fills attention and makes each detail seem separate. A familiar routine may leave so few new records that an entire stretch of time becomes compressed in memory. The seconds did not change their local duration. The observer changed. And perhaps this is where the search for a universal present finally becomes personal. At the beginning, we asked what is happening right now on the other side of the universe. The question seemed to ask for information about a distant place. Somewhere beyond the Milky Way, stars are forming, galaxies are colliding, and worlds may be moving around suns whose light has never reached Earth. Surely, we thought, all of those things must belong to the same moment as the clock beside you. Relativity made the answer less simple. A distant now depends on how clocks are synchronized and how the observer is moving. Two observers passing each other can construct different present moments across a large distance, even though both follow the same physical laws. The disagreement does not make reality subjective. It reveals that the universe has not supplied one privileged way to gather distant events into a single present. The present is dependable where paths meet. It becomes a coordinate choice when extended across space. Then the clocks themselves separated. One traveled and returned. Another remained on a different path. They met again carrying different readings, although neither had malfunctioned. Each had measured the proper time of its own world line. Gravity deepened the difference. A clock higher above Earth accumulated slightly more time than one below. Near dense stars and black holes, the differences became larger. Space-time was no longer a fixed background. Its geometry helped determine the duration recorded by every clock moving through it. The idea of one cosmic rhythm became harder to preserve. Then entropy gave time a direction. A glass fell and broke as heat spread, waves moved outward, and the event left traces in its surroundings. The basic microscopic laws often allowed both temporal directions, but the conditions of the universe made one direction overwhelmingly familiar. The past left records. The future did not. Memory carried those records into the present. The mind did not look backward through a window in time. It reconstructed earlier events from physical changes existing now. Every remembered voice, room, and face depended on a present pattern formed by earlier interactions. This gave the local present a special texture. It contained inherited traces from one direction and unfinished possibilities toward the other. Finally, the master clock disappeared from the deepest description. When gravity and quantum theory were pushed toward the same framework, time could no longer remain an unquestioned external variable. The universe could not be placed beside another clock outside itself. Change had to be described through internal relationships. One physical process could act as a clock for another. A sequence could appear in correlations, even if the complete state was not moving through an additional external time. None of these steps prove that time is an illusion. The clock still ticks. A body still ages. Signals still travel. Causes still precede their effects along every physically allowed path. The loss concerns a simpler picture, the picture in which time is one invisible current carrying the whole universe forward together. What remains is quieter and more local. There are events. There are world lines connecting them. There are clocks measuring duration along those paths. There are light cones defining which events can influence one another. There are physical records carrying earlier conditions into later ones. And there are observers, built from those same processes, experiencing one event at a time. You are one of those observers. Your world line has passed through every place you have ever occupied, even though the person listening now remembers only a fraction of them. It has crossed rooms you no longer see, mornings that disappeared without leaving a clear image, and nights that once seemed as immediate as this one. Those earlier events do not need to remain visible for their effects to continue. Your language came from them. Your habits came from them. The shape of your body and the structure of your memories carry parts of their history. The past survives through what it changed. The future will also be connected to this moment through whatever happens here, although the present contains no ordinary record of those later events. A small decision may alter a nearby part of your future light cone. A breath changes the chemical state of the body. A movement changes the pressure against the bed. A sound passing through the room changes the ear and nervous system. Nothing in the moment is detached from the rest of the path. But the path does not need to be controlled from outside. There is no requirement that you understand the whole geometry before inhabiting one point within it. A person does not need to calculate Earth's orbit before feeling the floor beneath their feet. A clock does not need a map of spacetime before measuring its local duration. And the mind does not need a universal present before resting inside this one. The distant universe remains beyond immediate reach. The light arriving tonight may have crossed space for years, centuries, or much longer. It carries old information into a younger observer. Some of the sources that emitted it may already have changed beyond recognition. A star visible in the sky may no longer have the same surface it had when the light began its journey. A galaxy may have moved, formed new stars, or changed shape while its older image continued toward Earth. There is no way to see its distant present directly. But the arriving light still creates a relationship. An event near that distant object sent a signal. The signal crossed spacetime. It entered a detector, a telescope, or an eye. The remote past became part of a local present. This is how the universe makes contact with itself. Not through one shared now, but through signals and interactions connecting one event to another. Every observation is a meeting. Light leaves one world line and reaches another. Clocks separate and reunite. Particles collide. Bodies exchange heat. Memories form because an event touches a system capable of preserving a trace. Reality may be understood less as a collection of things existing together at one moment, and more as a network of such meetings. The things still matter. The stars, clocks, bodies, and rooms are real. But their histories and relationships carry much of the structure we once expected absolute space and time to provide. This can make the universe sound lonely. Each observer possesses only a local present. Distant events arrive late. No viewpoint sees the whole cosmos as it is now, because no observer-independent cosmic now has been given. Yet the same structure that limits us also connects us. Light can cross the distance. A signal sent here can become part of another observer's future. Records can survive their makers. A clock can leave, travel, and return with a history written into its reading. Local does not mean isolated. It means that every connection must have a path. The room around you is filled with paths. Warm air rises and cooler air moves beneath it. Faint light reflects from surfaces before reaching your eyes. Sound travels through walls, floorboards, pipes, and open space. The clock's internal parts continue their repeated motion. Your heart follows a rhythm that has never been perfectly regular, but has carried the body through every remembered day. Each process has its own pace. For a while, they meet here. That may be enough to explain why the present feels so immediate. It is the event at which these paths currently intersect for you. The past is represented through the structures that arrived here. The future is represented through tendencies, plans, probabilities, and paths that may leave from here. The present is not a sheet crossing the universe. It is the local meeting point of what has arrived and what can still depart. Even that description does not solve the philosophy of time. It does not choose finally between presentism, eternalism, a growing block, or some theory that has not yet been developed. It does not prove that consciousness creates the present, or that the present is absent from reality. It gives us a smaller claim, one close to what physics can support. Nature provides local events, proper times, causal relationships, and records. A universal moving now is not required by the theories that describe them. The rest remains open. And an open question does not always need to be uncomfortable. There are questions that keep the mind awake, because they demand an immediate answer. There are others that become gentler when the need for an answer is released. Time may belong to the second kind. You do not need to decide tonight whether the future already exists. You do not need to picture the whole of space-time. You do not need to imagine the equations beneath every ticking clock. The nearby moment continues without that effort. Your body already knows how to inhabit its world line. It receives what reaches it. It changes in response. It carries some of those changes forward. The clock beside you will continue counting whether you listen to it or not. At some later event, its display will show another number. The room may be brighter. The sounds outside may have changed. The person beside the clock may be asleep. No universal clock will announce that transition to the cosmos. It will happen locally, through the quiet development of one physical state into another. And when morning comes, it will not arrive everywhere. It will arrive along one horizon, for observers carried by one rotating planet around one ordinary star. Elsewhere, other clocks will follow other paths. Other worlds, if they exist, will have their own days and nights, their own signals, and their own local versions of now. The universe does not need to gather them into one moment for any of them to be real. Perhaps that is the simplest lesson hidden inside relativity. Reality does not wait for every clock to agree. It only requires that when paths meet, their histories fit together. The clock beside you has followed its path faithfully. So have you. For this moment, the two paths remain close, moving together through the darkened room, while distant stars send old light across distances that no single present could ever contain. If you would like another quiet journey through the questions hidden inside the night sky, you can subscribe and return whenever you are ready. Until then, there is no need to hold the whole universe in one moment. This small one is already here.